Filippo, good morning. Oleg Naimark is speaking.
Yes, nice to meet you.
Nice to meet you also. Best wishes from snowing Urals in Siberia.
Yes, the same. Here in Rome is quite warm, so
okay. How are you? Yes. How are you?
And is it okay for you to manage this section? I will support technically if there are issues, but I think it's more related to your work. So.
Okay, I think it will be nice, but we need to discuss some technical aspects, because the first speaker will be Irina Bannikova. Is it possible to test, since we have a few minutes, demonstration for her? As I understand, you need to pass the rules for her. Okay, Irina Bannikova is the first speaker.
Okay. But so do you want to chair completely the session or no?
No, maybe we will split with you, because some presentation will be from our team.
Okay. So I can manage the presentation for your team.
Yes.
Okay.
I would appreciate if.
Yes. Perfect. Yes,
you could start the session.
Yes. Okay. Thank you. Yeah, I will do that. No problem. And after that, if you have issues in the other presentation, I'm here to support you technically if there are some technical problems. And
okay, thank you.
Francesco is also here with me, so we will.
Hi everybody. Hi.
Good morning, Francesco.
Good morning. Good morning, Francesco.
I think in 2 minutes we can start, so we have to respect a quite tight schedule.
Yes. Irina, is it okay with you?
Yeah, everything is okay. Yes.
Okay, Irina, we see your presentation.
Yes. You can put in presentation mode if you want.
This is
Yes, it's perfect.
Yes. Next.
Yes.
Okay.
Everything is working. Yeah.
Okay.
So I think we can start the section, and what it is important to remember to all the authors before thanking them for being here today early in the morning is that we have to respect this a bit tight schedule, because we had more participants than what we expected at the beginning. So we have 10 minutes for every presentation. I mean, ideally would be 8 minutes of presentation and 2 minutes of questions, but of course we will see how it will go. And so it's my pleasure to introduce the first speaker. The title of the work is Scaling Laws in Fragmentation Dynamics of Ceramics and Natural Materials. The authors are Irina Bannikova, Sergei Uvarov, Vasily Chudinov, and Oleg Naimark. I hope my pronunciation was correct. And thank you, Irina, for making this presentation for us.
Thank you very much for my presentation in our conference. Good day, ladies and gentlemen. I am presenting a paper, Scaling Laws in Fragmentation Dynamic of Ceramics and Natural Materials. The work is carried out at the Institute of Continuum Media Mechanics Ural branch of the Russia Academy for Science in the Laboratory of Physical Foundational Strength. This is slide outline of the report. One, papers and motivation of the research. To review so the result of our laboratory work on the fragmentation of ceramics and nature materials, quartzites, quartz, sandstone, under various loading conditions and method of recording the processes of deformation and fracture. Review of the methodology for size or mass, fragmentation analysis, and fractal luminescence registration. For result of fragmentation analysis and fractal luminescence signals and analysis of the initial porosity of sample and the fracture surface of fragments. And conclusion. In introduction, the problem of fragmentation is fundamental of foliage groups of physical phenomena at scale, from ductile and brittle failure of materials. The fragmentation process exhibits the signal of a critical phenomenon and responsible scale laws. It implies the analysis of materials behavior depending on the loading energy near some critical point, which corresponding to the transition from materials with damage to fragmented materials. The critical behavior is fragmentation is investigation by analysis, statistical fragments distribution depending on the material properties, ductile, brittle, its initial structures, porosity, loaded intensity. The fragmentation law describes the spatial temporal dynamic of defect evolution with class of singularity and the final stage failure, which is typical of lower equilibrium critical system. The statistical fragmentation laws are associated with basic aspect of failure related to the nature of the singularity typical of critical phenomena, which are component in the case of failure by defect nucleation and near multi-scale interaction leading to the crack, nucleation and growth. As applied to fragmentation, this is manifested in qualitative change of fragment size, mass, statistical distribution depending on the material structure and loading intensity. The imperative defined statistical fragmentation laws as described by an exponential, logarithmically normal and power law distribution. The goal of our work is to experimentally study the fragmentation of ceramics and nature materials under various loading conditions and method of recording the processes of deformation and fracture basis on the study of the distribution laws of fragment size under condition of quasi-static and dynamic compression with joint registration of fractal luminance, shock wave loading. That will be contribution to the establishment of the relationship between self-similar laws of deformation and fracture with multi-scale mechanism of fractal relaxation caused by the behavior microscope defects. The all parameter of sample, ceramics, quartzites, and quartz has piezoelectronic properties, and since then are presented with this slide. By methods loading are presented on this slide in table below. For testing a sample which has piezoelectric properties was selected. Impulse loading was realized by the method of electric explosion of wire, including electrical scheme of electric explosion wire and photo of the experimental complex are presented on the slide, and includes a system of capacitor, a source of high voltage which provides electrical explosion of wire, and the formation of the shock wave propagating in the radial direction. The amplitude of the loading pulse was set by changing the energy on the capacitor battery. Quasi-static compression realized of the electromechanism universal testing machine performing any axial loading. Fractal luminescence was registered by two methods. In the first, the joint operation of the photon multiplier and oscilloscope was used. In the second, high-speed video camera was used, which recorded the destruction of the sample and fractal luminescence. Dynamic loading of cylindrical sample by a Compkinson Colston bar setup. Fractal luminescence was registered by photomultipliers and oscilloscope. The destruction processes of rock quartzite cylinders was accompanied by fractal luminescence. The gloss was recorded in two ways, with photomultiplier and high-speed camera, with which was able to record the destruction processes itself. The resulting specimen fragments were identical in shape and size, regardless of the loading conditions. Sample fragments were sieved across sieve system and waves. The total number of fragments was counted on each sieves. This slide shows cumulative fragments distribution for quartzite sample obtained under quasi-static and dynamic loading. The curves have two slopes. Each load is described by a power law, which is typical for the distribution of brittle material. For large fragments, the power in the law was same for all samples. For small fragments, the degrees were different. Part of the curve runs below. This is possibly related to the formation of the fragments as a result of the large fragments break. We analyzed the time interval between fractal luminescence pulse obtained by photon multiplied and an amplitude of present is my slide on the signal responsible to noise. Fig 10 shows the cumulative distribution of the number of time interval greater than a central specified from time interval between dumping of pulsed of the entire signal. For all sample of quartz, next sample investigation, the cumulative fragments mass distribution have a slight inflection and were well described by power function with a height approximation confident of R in degree 2, 0.96. We analyze the time interval between photoelements pulse obtained by photomultiplier. The figure 12 shows the cumulative distribution of the number of time intervals greater than same specified from the time intervals between the pulses of the entire signal for sample 3 and the second part of the pulse for sample 5. This is shows the cumulative fragments mass distribution for sandstone samples obtained under dynamic loading. The curves have to slow with a small inflection obtained and different loading energize. The cumulative distribution are described by a
sorry,
function.
Irina. You need to go to the conclusions because we have a lack of time.
Okay.
Sorry for interrupt you.
Okay. And in conclusion, the result of the work are shown on the slide. Thank you for your attention. I'm sorry.
No, thank you so much. It's quite normal with the short time to be short in the presentation. It's okay. And I think if the audience has some question, we can make it in the chat, so we can go to the next speaker, and so we can respect the time. And I will leave the floor to Professor Neymark to chair the next speaker.
Thank you very much, Filippo. I would like to say and to thank Irina, because I need to say to our audience that Irina made the presentation from hospital where she with daughter, and we wish for you and for your daughter the good health.
Yes, of course. Thank you so much. And actually the topic is very interesting, so
yes,
congratulations.
Yes, thank you very much, Irina. Let me please to introduce the second speaker. It will be Alexander Nikitin with the presentation, the modeling of special crack growth in smooth specimen in very high cyclic fatigue torsion conditions. Please, Alexander.
Okay, hello, thank you very much for your introduction. I still need some authorization from you to share my screen.
Yeah, Irina, you have to remove your presentation.
Okay.
Stop sharing.
Yeah, and today.
Stop sharing.
Yes.
Okay.
Perfect. Yes. Yes. Thank you.
Okay. Thank you. And I hope that everything is okay now.
Yes, Alexander, please.
Okay, good. So my talk is about the modeling and of their spatial crack growth under the very high cycle fatigue loading under pure torsion. So just a second, what happened? Okay, the brief introduction is the following. First, I will say a few words about torsion. After, I will show you experimental procedure and materials, results of very high cycle fatigue test on pure torsion, some details about the model and result of numerical simulation. I will try to be quite short too. So it's very important to perform some very high cycle fatigue test in torsion. You know, even for car industry, right now we have a very long fatigue life, about 10⁸ cycles. If we considering another application, something like aerospace application, so we'll go to 10⁻10 or even 10⁻11 number of cycles. So, and every time you have some rotation for blades for other applications. So torsion is very important subject for experimental investigation. So here you have a set for torsional test. Right now we use a direct pure torsional system presented on the slide. So, and we are sure that our loading condition are good because we are still working at low temperature, constant amplitude loading, and we can perform perfect calibration with a strain gauge presented on the right. So, and based on the procedure that we developed for torsion test, we perform very high cycle fatigue test at 20 kilohertz in per torsion for titanium alloy. The details of titanium alloy is presented here. So, and it's very interesting to test this material because it has not some non-metallical inclusion. So, for example, the first results for steels show that sometimes we have subsurface crack initiation with the inclusion. Here, in case of the titanium alloy, we don't have an inclusion and still have different types of crack. Here, I present you briefly the results of experimental test on material. So here on the right, you have a push-pull test on the same titanium alloy. It's an axial test. And we use the equivalent stress to calculate the results of torsional test here. You see torsional. So they are pretty good, match each other. And if we have a look on the lateral surface of the specimen, we have normally two types of crack. Sometimes we observe that just a single main crack lying in the plane of 45 degrees. Sometimes we have a double crack here, so that similar to the X shape. And we was trying to investigate what is the difference in the spatial shape of the crack, depending on the mechanism of crack initiation. Here you have a little bit more details of the crack growth, and we have to pay attention that during the initial state, we have a small part where a crack is growing in the plane of maximum shear stress. So it means that at the initial state, we have a pure shear as a driving mechanism for crack opening. If we have a look on the fracture surface, we can see that there are two types of cracks. The first crack is starting from surface, and we call it surface crack initiation. On the left, you see it's quite similar to the classical high cycle fatigue with a manufacturer roof morphology. And the second type of crack under the very high cycle fatigue torsion loading is a subsurface crack initiation. When we observe the crack initiation seat, we did not find any non-metallical inclusions. So it's just a feature of microstructure leading to the subsurface crack initiation. And as you can see, it's far from surface. It's about 600 microns from subsurface. So it's quite unusual because the maximum torsional shear stress are acting at the surface here. So, and in this case, we have two cracks, one developing in the plane of one orientation and second one perpendicularly starting from surface. So, and when we have a subsurface crack initiation, usually we observe X type of cracks. So, and in order to better understanding this phenomena, we try to apply the numerical simulation and try to modulate the crack with a different crack initiation seas. Here are some details about the models that we use. We use an idea of the full SN curve with the left and right branch. Right branch is relating to very high cycle fatigue. Left branch, we relate to the classical mechanism, mainly for high cycle fatigue, because we are always working at a relatively low stress amplitude here. So, and in this case, we extend our knowledge about the high cycle fatigue to very high cycle fatigue. And we introduce the similarity in the shape of SN curve here. So, and we introduce the kinematic equation for damage function. It means that we the material locally at the local point, and we follow the degradation of material, and after link the degradation of materials that we described by damage function with a elastic moduli of material. Here we have some details about this model, and we associate that this degradation of material could be led by the normal crack opening and shear crack opening. And during our calculation, we use a double step verification. So we check the stress state with one criteria, that is a Smith-Watson-Toppler, and with another criteria, Carpentieri-Ventadori-Spagnoli, that is describing the shear crack under the tension. So, and here you have some details about numerical simulation. We used the special algorithm that allowing us to get the analytical solution for damage function at each time level and each point. So, and finally, we built the 3D model. We use ANSYS for calculating the stress state. We can make calculation in elastic assumption or elastic plastic. So elastic plastic is very long, and here I present just elastic solution. So we calculate the stress state with ANSYS after we apply our algorithm to calculate the damage function, and use the kinematic equation to describe the evolution of damage. And
Alexander, I am sorry, time is short.
Okay, so, and here the green color introducing the quasi-crack. So, and we get the crack initiation from surface after we put additional hard element inside, deeper and deeper, and we got the X-type crack with the two perpendicular. So, and finally we arrive to conclusion. I can say that we observed two types of crack, surface, subsurface, and we introduce a model based on damage theory. And applying this theory, we are capable to predict some special features of crack initiation under very high cycle fatigue. That's all. I think.
Alexander, thank you very much. Thank you very much for consistent presentation. But the time is lost, and
okay.
Thank you very much again. And Filippo, please, you have rules now.
I will stop my presentation. Okay.
Yes, stop your presentation, and after that, there is the next speaker. You can introduce him, Professor Neymer.
Okay. So sorry, I have to go for lecture.
Filippo, yes. Since yes, again. The next talk will be given by Dr. Mamdar. Yes, prediction of the displacement mechanisms using neural network. Please.
Good morning, Professor.
You can share.
Yes, I'm going to share, but yes, there's some problem here.
No. There is the green button in the center.
Okay.
Yes. You are now sharing, but you have to share the presentation. You are not sharing.
Yes, there is some problem.
Now you are sharing. But you are sharing the program and not the presentation. You have to put in the screen your presentation. Now you are not sharing. If you want, we can go to the.
Okay.
We can.
Is a start. Can I start?
Yes, yes,
Okay. Okay, I move fast because time is
yes.
very limited.
Thank
The
you.
prediction of displacement mechanism of the cracked soil using nonlinear extended finite element method and artificial neural networking. What we have here for introduction, based on the previous research investigation, the crack in different type of material show different behavior. For example, in the metal and in the stone and wood, they have different type of the crack initiation and propagation, but in the soil a little is changed, especially when we have the clay soil. In the clay soil, what we have, based on the mechanical property of the soil, we have a starting crack. When load is applying to that, this kind of the crack will be extending. Objective what we have here for this investigation is to simulate crack propagation and crack morphology, and to realize the impact of soil crack morphology on a displacement and vibration mechanism of the soil foundation, and finally to estimate soil foundation seismic failure pattern. We had different steps here from starting of the problem. What is here is the methodology. We use two methods. First, a non-linear extended finite element method analysis and artificial neural networking. This is two main tools we use here, and using MATLAB programming to understand and prediction of the crack morphology and displacement prediction. We had two models, model 1 and model 2. In both models, the geometry are same. We have one geometry here, and magnitude of applying force for both models are same here. We applied acceleration in all directions, in 3 directions simultaneously. What is different in these two models? In first model, we use a soil A, and in second model, we use a soil B. The soil has been collected from the literature, what we have here. And finally, what we find after running the experimental, the first model, here we have before propagation of the crack and after the crack propagation. The first model, the model 1, the tip of the crack is almost is different, and then the second model is also a different type. We have one animation here to show how this kind of the crack is the propagating. Then when we are running the software, we have here the crack for the first model. The crack is starting in 4 different steps. First one is here, second and third and fourth. This is the first model what we have here. And for the second model, after the running the software, August software, what we have here, we have the crack. It is the first step of the crack propagation. In both models, as I mentioned, the geometry and applied load are same, just mechanical property of the soil is different. Then this is what we have here in the second slide, the failure pattern of the model 1 and the model 2. We have 2 different patterns. In the first model is the sliding based on the fractural, and second one is with the sliding of the model. After MATLAB and writing artificial neural networking and base of test, train, and validation, we have 2 different differential displacement for this model, and this is validation of and R and MSE for these 2 models. And finally, what we have here is the conclusion. And this is work I'm present. And if you have any question.
Thank you very much, Dr. Damdar. We have opportunity at least for one question. Please, somebody wants to ask? Felipe, maybe you have a question?
No, I am co-author, so it's better if I don't ask. I think it's fine.
Okay.
We can go to the next.
Yes, thank you very much,
thank you so
Dr.
much.
Damdar.
Thank you.
Felipe,
Thank you
the
so
next two presentations will be
Yes,
from
yes,
our
yes.
team. Please
Yes.
supervise.
Yes, the next presentation, the title of the next presentation is Scale Invariant Regularities of Fracture Surface Morphology in VT6 titanium alloy under very high cycle fatigue loads. Vladimir Oboring, Mikhail Vanikov, and Oleg Naimar. Sorry, it's not fatigue, it's very high cycle. No, it's very high cycle fatigue loads, yes. So, yes, please.
Yes, hello everyone. Thank you very much for the opportunity to speak at the conference. The influence of random statistic and dynamic loads on the lifetime of materials under very high cycle fatigue is a considerable current interest as to the reliability of estimating the strength of aircraft motor materials under real operating conditions. An example is the estimation of the endurance of gas turbine engine blades under the collision with the solid particles, what's usually called as a foreign object damage. In this work, we investigated the influence of consecutive dynamic and very high cycle fatigue loads on the lifetime of titanium, titanium 6 aluminum for vanadium alloy. The relevance of a problem statement is determined by the critical application, life estimation of materials and structural elements of aircraft gas turbine engines, expressing random dynamic effects under flight cycle conditions. And in this work, we investigated the effect of fatigue characteristic of titanium specimens that were obtained from a blade simulated that underwent the entire complex of technological operations in the factory. This slide shows how the specimens were cut from the laboratory simulators of the blades. Dynamic preloading of titanium alloy specimens was realized using the split Gopkinson pressure bus setup, after which the specimens were subject to cyclic loading. Here you can see the split Gopkinson pressure bus setup. It's shown how the specimens are installed between rods, and specimens are shown after testing. Fatigue tests were carried out using the resonance type of testing machine of Shimadzu USF 2000. This machine provides 10 in power 9 up to 10 in power 10 loading cycles with the amplitude from 1 to several dozens of microns and frequency of 20 kilohertz, which reduces the testing time in the comparison to the classical fatigue testing machines. The cooling of the specimens was realized by compressed air. This slide shows the dependence of the stress value on the lifetime to failure after dynamic preloading and specimens cut from a simulator blades. It has been found that the fatigue failure stress of the preloaded titanium alloy decreases from the stress level of 460 megapascal to 130 megapascal, which corresponds to the critical number of cycles 10 in power 8. For the titanium alloy specimens cut from a simulator's blade, the results of tests showed 37% decrease in the ultimate stress failure from a stress level of 476 megapascals in the initial state to a stress level of 300 megapascals, corresponding to the critical number of 10 in power 8 cycles of loading during air cooling. This slide shows characteristic surface relief of a fatigue fracture zone for high and very high cycle fatigue. For the specimen subject to cycle loss in the range exceeding 10 in power 9 cycles, the crack formation is started inside of a specimen. The fracture surface, in this case, exhibits a fatigue zone known as a fisheye, which is a particular feature of such fatigue regimes. The center part of this region comprises a fracture nucleus surrounded by the region of submicrocrystalline structure. We used the new view interferometer profile of high structural resolution for qualitative fracture surface analysis, which provided the data allowing us to find correlation between mechanical properties and scale invariant characteristics of damage-induced roughness formed under high and gigacycle fatigue loading conditions. The approach to characterization of the fracture surface morphology in terms of spatial invariance was proposed by Zeiser and Bouchot. The function K of R is calculated for one-dimensional profiles of fracture surface relief according to the Formula 1, where K of R is the average difference between the values of surface relief heights in the window of size R, and H is the Hauss exponent. Representation of the function K of R in logarithmic coordinates allowed one to evaluate the lower boundary of scaling range L min and value of upper boundary, considering one as the characteristic scale of the process zone L max. That's the area of correlated behavior of multi-scale defect structures. A comparative analysis of scale invariant characteristics of specimens made of titanium alloy in the initial state and after high gigacycle fatigue loading allowed us to establish the constancy of Hauss exponent 0.6 in a wide range of spatial scales, 0.8 up to 47.9 microns. We use special scales for writing the kinetic equation for the crack growth. The kinetic equation for the crack growth, del over dn, is a function of phi of delta k, stress intensity factor E, Young modulus, and L scaling correlation scale in the ensemble of defects, and LPZ, the scale related to the process zone. The function dividing both sides of kinetic equation by L scaling, we have a similar Paris law, where alpha is a universal exponent. The function K of R in logarithmic coordinates allowed one to evaluate the lower boundary of a scaling range L scaling and the value of upper boundary, considering one as the characteristic scale of a process zone, LPZ. That's the area of correlated behavior of multi-scale defect structures. And finally, the results are given in these slides. And thank you very much for your attention.
Thank you so much for your nice presentation. If the audience have questions, we are open for discussion. We have time for a quick question. I think we can respect the schedule and go to the next speaker then. And I want to thank you again, Professor Vladimir Oborin, for this nice talk. And I leave Oleg to introduce the next speaker. Otherwise, I can make it. Okay, I can introduce the next speaker. The next speaker, the title of the next presentation is Staging Analysis of Damage Failure Transition in Composite Material by Optic Fiber Acoustic Sensor. And again, the team of work is led by Professor Oleg Neymark.
Okay.
So you can start.
Thank you very much, Filippo. Have you seen my presentation?
Yes, yes, yes.
Okay. I would like to follow the following content, and the goal of my presentation will be the comparative analysis of our experimental data for piezoacoustic and optical acoustic tests in composite materials to investigate the damage staging and corresponding analysis of data. And I think that the comparison of these two methods could be very attractive for application, because optical acoustic data could be used for in situ registration in different construction and also in laboratory tests. And I would like to pay also attention concerning interpretation of experimental data from point of view of duality of damage failure transitions in the linking with two-parameter fracture criteria. And just very briefly to show some perspective with application of X-ray synchrotron tomography. Okay. Yes, on these slides you can see the main steps for study of optical acoustic testing and using piezo and optical acoustic setups. On the up corner, you can see the optical scheme that was realized for testing of the sample in laboratory conditions. And in this picture, it's the embedded fiber optical setting. And it's very important for realization of this experiment also to protect the ends of optical fiber ends to record data during experiments. And typical picture for registration of signal using piezoacoustic data and optical acoustic data, you can see in the down corner. On these slides, you have the illustration of characteristic stages of the preparation of the samples for the following experimental study to record data, in situ data of damage evolution in the sample during the uniaxial tension. Some comments concerning procedure of the data proceeding, of data processing. You can see the data from 3 channels, 2 conventional piezo acoustic channel 1 and channel 2, and the channel 3 is the data from optical fiber acoustic registration. With characteristics concerning the accuracy, and it's very important that the first channel is called master channel because it was established at some threshold for discrimination of the signal, and 2 channels, channel 2 and channel 3, were triggered using the signal from the channel 1. Concerning the method of processing of data, we have used several methods to analyze the staging of damage failure transition. And the first one, taking into account the presence of finite amplitude disturbances of energy in piezoacoustic signal and optical sensor data. The first step of our analysis was the attempt to find some features of self-organized criticality. But not all features of this phenomena that is very typical for this kind of the dynamics were found, but at least 3 of them was very clear to show that the finite amplitude disturbances in acoustic signal could be responsible for different stages of damage failure transition. It's the power law distribution, instability of the integral characteristic of criticality, and we have knowledge what is the parameter, and of course nonlinear interaction, which determine the threshold nature of this phenomenon. And what kind of the analysis was carried out? First of all, we try to analyze according to Grasbeck-Prokach embedded dimension. But the estimation of embedded dimension did not allow us to establish the features of dynamic house, because too many dynamic modes were found that correspond to the self-igniting criticality scenario. And as a consequence, we decided to analyze this signal using so-called recurrence quantification analysis to estimate two characteristic parameters. It's so-called laminarity and deterministicity. And the analysis of data in terms of this characteristic allowed us to establish very pronounced power laws for energy, and in terms of cumulative distribution function to analyze the signals, and the estimation in the term of I'm sorry, yes, of laminarity and determinism parameter allowed us to make the following conclusion: that stages of damage failure transition includes pronounced stochastic parts, which corresponds distributed damage accumulation in the bulk of the sample, and then deterministic related to nucleation of the crack in composite materials. And it was practically the goal of our analysis. Why? Because the previous our research for composite materials with the hull, with concentrator, when we analyzed DIC and acoustic emission data in different places for different spacing from these hulls for concentrated, revealed two characteristic pictures in the phase portraits corresponding to distributed damage. You can see this in this part. It's typical phase portrait in terms strain rates versus strain. And you can see two attractors related to distributed damage and attractor related to crack nucleation. And it corresponds exactly to our theoretical consideration that phenomenologically can be related to duality of fracture criteria in terms of critical stresses and material fracture toughness. And according to our knowledge, it corresponds to characteristics of similar solution related to specific kinetics of damage accumulation and crack propagation. And it's in perspective of our research, because composite structure, we have opportunity now to use powerful setups for X-ray tomography, when we could investigate porosity distribution and clusterization of porosity, and the processing of this data after X-ray tomography allowed us also to establish characteristic features of damage distribution for first stage and transition to crack initiation to the second stage. And very short conclusion related to the current results and perspectives. Thank you very much, Filippo.
Thank you so much for the nice talk. I have only a curiosity that is linked probably to my lack of knowledge about composite material, but do you know, according to your experience, is possible also to apply these methods to more complex structures? So if you have geometrical discontinuities, how efficient or effective is this method in this case?
I think so, because like acoustic emission methods, optical acoustic tools also could be applied to this kind of the statements. Yes, I think so. I think so.
Okay. Thank you so much.
Mm-hmm.
Thank you.
Thank you. Thank you very much.
Thank you. So you can now introduce the next.
Yes.
You can be the chair again, and I will manage the presentation where you are co-author.
Yes. Okay. The next presentation will be given by Dr. Tibari, mechanical behavior and damage analysis of the chlorinated polyvinyl chloride. Please.
We are not able to hear you.
Yes, it's true.
Yes, now yes.
No, it's me, Felipe. It's not presenter.
Okay. We don't hear anything from the speaker of this work. You have to unmute.
Dr. Tibari, are you here or not? Nadia.
Hello, everyone.
Okay.
Hello, everyone.
Dr. Tibari, is it you?
Yes.
You could start?
Yes.
Okay, we could start.
Yes.
We could start.
Yes. Thank you very much. Thank you. I'm very happy to start with you my work entitled Mechanical Behavior and Analysis of Chlorinated Polyvinyl Chloride. I start my work by introduction, experimental details, result, and discussion, and I finish by conclusion. So, the CPVC is a thermoplastic polymer used for the supply of cold and hot water. The specimen for tensile tests were prepared according to ACM standard D638 method of test for tensile properties of plastic. We use Einstein H8L1 machine. The result in this work is shows in figure 3. We can observe that the three strain properties of CPVC are sensitive to temperature. At low temperature, -10 L and 10 degrees Celsius, the plasticity of the material is reduced, meaning that it is less able to deform before breaking. At room temperature, the plastic deformation is significant. At higher temperature, the ductile fracture increases the breaking stress. For these results, some of the most important tensile properties, such as yield stress and Young's modulus. The figure 4 illustrate the evolution of yield stress with various temperatures. From this figure, the value of yield strength decreases with increase in the temperature. At low temperature, -10 L and 10 degrees Celsius, yield stress is relatively high. At room temperature, the yield stress continues to decrease as the temperature increases. At high temperatures, the yield stress is lower than a lower temperature. This reduction can be explained by the positive impact of molecular mobility. The evolution of Young's models is shown in figure 5. The value of Young's models decreases with increase in the temperature. This reduction can be explained by the thermal expansion. We encourage the molecule and the CPVC material to vibrate more, leading to an overall decrease in stiffness. The static damage model is based on ultimate stress. The figure 6 illustrates the evolution of static damage according to life fraction. We observe that the damage accelerates with increase in the life fraction. We can also remark 3 stages of damage. The first stage damage is initiation damage, is between 0 and 20% life fraction. The second stage is the progressive damage, is between 20 and 78 life fraction. The life fraction become critical in the value 78%. In the third stage, the material is out control. In this stage, you must change the material. And finally, we found that the mechanical behavior was affected by the temperature. The models of elasticity and yield stress are decreased and the temperature increased. The static damage with increase in life fraction. The life fraction become critical at value of 79%. Merci. Thank you for attention.
Thank you very much. We have at least 3 minutes for questions. Please, our audience, I think it could be questions.
I have a question.
Please, Felipe.
Yes. Which kind of application are you thinking dealing with this study? So, where this study can be applying in some practical application, and which is the impact on this?
The impact of temperature in mechanical behavior of CPVC is important. The yield stress and Young's models decrease with increase in the temperature.
Okay, but which kind of, engineering applications are you considering for this?
The application of CPVC is the supply of cold and hot water.
Okay, thank you. Thank you so much.
Since we have time, let me please also, what kind of the damage characteristic are you using to investigate different stages of damage Fourier transition? What kind of the parameter? It's like that?
The damage is the static damage is based on ultimate stress.
Okay.
And yeah.
ultimate stress. Yes, I understand. Thank you. Please, another questions? Thank you very much for your interesting talk. We could go to the next. The next presentation will be given by Dr. Panayotis with co-authors, investigating color on archaic architecture with some specific aspects that presented in the title of the talk. Please, Dr. Panayotis.
Good morning to everyone from Athens, Greece. Can you hear me?
Yes.
My name is Franzi Yassimi, and I'm going to make this presentation.
Okay.
Our presentation is focused on the results of our preliminary investigation of the remaining traces of polychromy preserved on the cover tiles from the roof of Pisistration Telesterion, an important 6th century before Christ cover tile, ancient Greek ritual building dedicated to Demeter and Kore. Firstly, I will introduce you to the Telesterion, and they are in the aerial view. You may see the top view of the buildings in its current state. The building is located in the renowned archaeological site of Elefsina, as we call it, west of Athens. Here, if you can see, Elefsis. And this is the red line depicts the way from Athens, from ancient Athens to Elefsis through Hieraudos. And this is the topographical plan of the archaeological site of Elefsis. And the red line here is the Telesterion we can see here. The sanctuary of Elefsis has been one of the most significant religious centers in antiquity. The main building of the late archaic sanctuary, where the Eleusinian Great Mysteries took place, the Telesterion, was built out of highly worked limestone, while its foundations were constructed with harder reddish limestone. From Frederick Noack, a German cultural historian and author, 1927, we learn that the walls of the nave, the columns, and the entablature were constructed out of limestone. It is not certain whether there were triglyphs and metopes. It is certain, though, that cima and roof tiles were made of Parian marble. According to Orlandos, numerous fragments were found from the roof of the Pisistratio Telesterion. Apart from the cover and the tiles, the most important part of the roof is the cima's corner, the upturned edge of the roof with the gutter in the shape of an archaic ram's head. The proof that all these pieces belong together is the material of their construction, which is Parian marble, and their proportions. The fact that they belong to the Pisistration building is proven by the layer they were found in, and by the traces of burning they bear. The roof tiles were decorated with painted palmettes. Layers of blue and red colors are still preserved on the surface of the architectural members. Its marble-covered tiles or antefixes were decorated with palmettes on their front sides, composed of 11 fronts spreading out of a single base and volutes. Originally colorfully painted, as it is evidenced by the remaining traces of blue, red, and green on their surfaces. In certain pieces, the outlines of this decoration were clearly visible, as it documented in the drawing of Frederick Noack back in 1927. From the remaining traces of polychromy, it is possible to deduce that the fronts were rendered in bright red, outlined in blue, following the form of the carved stone. Traces of green are also visible on the palmette's base. The technological investigation of the antiphysis polychromy has focused both on the areas or spots that still preserve paint layers traceable with the naked eye, and those that were reported to beer colored decorations in the 19th and early 20th centuries literature, even though they are hardly visible today. The main objective of this project has to investigate the surviving color by employing non-destructive analytical techniques and to try to understand the original painting techniques used by ancient craftsmen for the application of color. At the first stage were performed such as visible induced luminescence, a well-known imaging technique allowing to map the presence of Egyptian blue on the examined surfaces appearing as glowing white, as you can see in this picture and also in this slide. Subsequently, two other portable instruments were used in order to determine the composition of the other pigments. A portable handheld FTIR spectrometer allowed us to collect spectra from pigments. A portable handheld FTIR spectrometer allowed, the spectra were obtained in the mid-infrared spectra range. This is from 5,200 wave numbers to 6,150 wave numbers with a spectral resolution from 4 wave numbers. Egyptian blue, calcite, calcium oxalates, and gypsum were identified. The presence of gypsum was identified at 1113, 1130, 1125, 1116, and 6,163 wave numbers. Egyptian blue with the characteristic triplet at 1,000, 1,050, and 1,160 wave numbers confirmed, and also peaks due to calcium oxalates were detected. Furthermore, several spot XRF analyses were performed using the portable XRF system Tracer 5G by Brooker. The XRF analysis results revealed that the major elements detected in the blue areas were silicon, copper, and calcium, while minor amounts of lead, iron, aluminum, and potassium were also detected in all spectra. In the spectra taken on the green areas, the major elements detected were sulfur, calcium, copper, and iron, accompanied by lead in some cases and silicon in 2 areas. The spectra collected from the red area showed major elemental peaks of calcium and iron, accompanied by minor silicon and potassium elemental peaks. As it was expected, XRF analysis confirmed the presence of Egyptian blue through the identification of calcium, copper, and silica. However, XRF increased...
I'm sorry. Please change your slides.
Why? Don't you see the...
No, up to now we see only the first.
Oh no, my God. Why are this happening? Okay. I must change every slide here. So this is the aerial view. Can you see that now?
Yes.
I don't know what problem is, what happened. This is the archaeological site, as I told you. And this is the depiction of the tower tiles that was decorated with palmettes and volutes. This is the VIL imaging. And here, but that we can see the Egyptian blue appears as bright white, as I told you previously. The FTIR. I'm sorry, but you didn't tell me earlier that I didn't know that you couldn't see all the slides. And I am here somewhere. So as it was expected, XRF analysis confirmed the presence of Egyptian blue through the identification of calcium, copper, and silica. However, XRF increased the possibility of the existence of malachite at the center of the antifixes. Additionally, the use of a lead-based undercoat seems probable, covering that lead is present as major element in some of the analyzed areas. The detection of an iron-based yellow in the antifixes base, originally painted in green, possibly identified as malachite, as the copper signal suggests, may be associated with the application of a yellow undercoat, serving to ensure a better adherence of the sandy green pigment applied on top and to achieve a warmer hue. And this is, we're talking about this area. So in order to gain further insights into the painting materials and techniques employed for the polychromy of the Lessinian antifixes, it is imperative to proceed with further microinvasive analysis on microsamples. Laboratory analysis of microsamples collected from the base and the fronts of selected antifixes would allow us to evaluate the exact gamut of pigments used for the decoration of the antifixes, to investigate on the stratigraphy of paint layers and their composition, to the original painting technique and the organic binder that was used for the application of paint layers, and the secure identification of lead white in the lead rich areas and its possible function as a filler or an undercoat, finally, on the exact composition of the yellow, red, and green pigments. Thank you for your attention, and I'm sorry for the problem.
Thank you very much for your very consistent presentation. To our deep regret, we have no time for the question. Thank you very much again. We will go to the next presentation that will be given by Salvatore Aiello.
Good morning.
Good morning. Analytical study of a circular plate with thickness anomaly, critical temperature fluctuation in the tunnel. Please.
Okay, thank you very much, but it doesn't work. I will share my screen.
Yes, please.
Okay. Do you see?
Yes. Yes.
Okay. So I'm Salvatore Aiello, and I'm a PhD student of Polytechnic of Turin, and I'm here to present our research titled The Analytical Study of a Circular Plate with Thickness Anomaly, Critical Temperature Fluctuation in the Tunnel. This presentation will focus on 5 points. First of all, the structural health monitoring techniques are crucial to ensuring the safety and reliability of our structures. By using advanced monitoring technologies to detect damages and predict potential failures before they occur. The monitoring results then are used to build an analytical model that provide insight into the structural behavior and help engineers make informed decisions about maintenance and repairs. By integrating structural health monitoring techniques and analytical models, we could optimize maintenance schedules and reduce costs. Looking to the future, the development of the new monitoring technologies and advanced analytical model will continue to improve the effectiveness of these techniques. However, I would like to start talking about the importance of this kind of techniques in our modern world, in particular with the increasing age of our infrastructures and the demand for the sustainable, safe, and reliable structures. It is critical to ensure that we are using the best tools available to monitor and maintain the health of our structures. Alongside the problem of aging, we can analyze the effects of decay, construction defects, aggressive external phenomena. The structural health monitoring techniques are a set of technologies that enable engineers to assess the condition of their structures, detect damage, and predict potential failures. Above all, it is unthinkable today not to introduce artificial intelligence techniques and make full use of non-destructive testing. Moreover, structural health monitoring techniques can be used to optimize maintenance schedules, reduce cost, reduce the interpretation subjectivity, minimizing the impact of business operations. The starting point of our studies were the results of the real monitoring campaigns in several tunnels in northern Italy, particularly the results of georadar campaigns. Ground penetrating radar, GPR, is an innovative and non-destructive testing method that is widely used for defects characterization materials. With a frequency range of 10 to 2600 MHz, GPR uses high-frequency electromagnetic wave impulse to penetrate materials and identify hidden geometries. The dielectric properties of the materials influence, of course, the propagation of such as impulse. The GPR surveys reverse local thickness reduction at the bulkhead of the tunnel. These thickness anomalies were caused by the complex topside of the lining, which made casting operations difficult to manage. The observed thickness is only 1/3 of the designated one. Due to this reduction, we investigated the effects of the thermal variation that have a significant impact on a stress test on the material. To better understand these effects, we investigated two analytical models. The first one is the simple one, which uses an equivalent beam of rectangular cross-section with anomalous thickness and constrained adherence. The second one is a two-dimensional model which uses an equivalent circular plate with an anomalous thickness and constrained adherence. Both models are subjected to the self-weight and a linear temperature change. It should also be noted that the tunnel lining are typical weakly reinforced and unlocked to the ductility that distinguish inflected elements. Even though the thermal variation of lining is one of the possible causes of collapses, not enough attention is paid to these thermal stresses. In particular, the temperatures inside the tunnel and on the surrounding ground vary. The anomalous thickness problem was considered by studying the behavior of a circular crown plus a circular plate, where the crown have the thickness of the designed thickness. Instead, the plate has the thickness, the anomalous one that the georadar detected. The two models were created by extrapolating the scheme of the typological section of the tunnel with the anomalous thickness in the key, and its definition was made possible by the following assumptions. The first one, the analysis are limited to the calotte portion. Next step is that the lining's curvature is assumed to be infinite. The lining portion considers are not stressed by the compressive force along the middle plane. The only force at the work are the vertical one, for example, the permanent load, and the terminal ones. The soil has a consistent and uniform temperatures, where the linear variation of the temperatures along the lining thickness shows that the internal one is higher than the soil temperature. Crown and plate deformation are governed by the function W in function of R, and the integration constants for the two elements were derived by setting the appropriate boundary conditions. And under the assumption that the thermal delta is the same regardless of the two elements, we obtain the fixed constants. Thanks to them, the two zones currently investigated in the two-dimensional model are at the center of the plate, R equal to 0, and at the R close to R1, where R1 is the radius of the zone with the thickness anomaly. The calculation of the delta T critical is based on several factors, including the thickness and materials properties of the plate, as well as the plate's diameter and the boundary conditions. Understanding these factors and how they influence delta T is really interesting. Here we can see the results of the one-dimensional model, where two critical temperatures can be defined according to the tensile limits reached in intradose fibers. The comprehensive boundary condition is reached when the difference between the temperature of the intradose and the temperature at extra in the extradose is equal to the critical heating. As a result of this boundary condition, the stress spreading in concrete generates the phenomenon of concrete spalling. On the other hand, the critical cooling is the temperature difference between intradose cold and extradose hot, where the self-weight term is negligible. The results of the two-dimensional model are shown in these slides. We can see that the critical cooling values were defined for different concrete classes and different ratio between the design thickness on the abnormal thickness. In particular, the values are calculated both in the center at R equal to 0 and the correspondence with the zone where the change in thickness occurs. The management of a database of tunnel temperature is a critical task that requires accurate and reliable tools to ensure safe and efficient tunnel operation. In this regard, a Python code has been developed that allows the management of a tunnel temperature database and the detection of a critical temperature difference that may require immediate attention from the society. The code utilizes two models to calculate the critical temperature difference. A warning value is generated when the received delta T values is greater or equal to the lesser of the critical values of the two models. This ensures that the manager is alerted to the potentially unsafe temperature difference that may affect the tunnel's operation.
I'm sorry, may I ask to approach to conclusion?
Yes. Okay. For the conclusion is about our current research and the future developments about this topic. For first step in the current research is the development of the FEM model to study these correlations and to understand how it's possible, how to discover the behavior in function of the dimensionless parameters. And for the future developments is to create an application, an operational application that exploits the tool presented and increase the FEM model with the model of an arc with abnormal thickness variations. Thanks for the attention.
Thank you very much. It's really very interesting presentation. Thank you very much again, and I hope that you will be happy in discussion with the audience. We could go to the next presentation that could be given by you Angarra with co-authors, numerical study of to high efficiency work conditions on the radius H rotor wind turbine performance.
Okay.
Are you ready, please?
Okay, I'm ready. I will share my screen. Okay, good morning. Nice to meet you all, the IGF conference participant. I will present my research entitled Numerical Study of Effect of High Efficiency Vortex Addition on Darius Rotor Wind Turbine Performance. This is the content that I will discuss in this presentation. Introduction. This is my background of the research. First, increasingly worrying climate change, and second, the need for electrical energy is increasing day by day, especially with the electrification of the transportation sector. And then the need for renewable energy to replace non-renewable energy source, which is not only the impact of its use, which is detrimental to the environment, but also the impact of the exploration. Okay, next. This is my objective and scope of the work. This paper will discuss the numerical analysis of WAVP Darius each rotor. This study aimed to determine the effect of the adding of high efficiency vortex on the performance of Darius each rotor wind turbine. The power coefficient, torque, and flow characteristic of the rotor from the variation are analyzed in this study. This is chapter 2, numerical setting and configuration. This is my geometry of Darius rotor. The turbine used in this study was a Darius rotor with blade profile is NACA 0015 airfoil blade profile. The geometry and dimension of the turbine is in this study referred to research by Song et al. The rotor diameter are 1650 millimeter and the chord length is 375 millimeter. The turbine installation are angle 0 degrees. The blades are attached to the hub of the rotor arm at the 30% of the chord length. And the turbine has 3 blades that rotate counterclockwise around the center. This is my simulation domain. The simulation is run on 3D numerical. This investigation contains 2 domains, namely the rotor domain and the stator domain. For the area around the turbine that is still affected by turbine rotation, we set it as a rotor domain with 1.5D dimension. Okay, next, this is my variation, that is high efficiency vortex generator geometry. The type of the vortex generation used is high efficiency vortex, which is generally used in heat transfer device and gas mixer. The EHP is installed at the chord line position 25% of the airfoil chord length. The height of this passive element is recommended to 80 until 100% of the boundary layer from the surface of the airfoil. The variation of this investigation of the study is geometry of the EHP, namely rectangular, trapezoidal, and triangular, and the type angle variation is 45 degree. This is my CFD modeling, preparation, and setup. The problem in this research was solved by the commercial ANSYS Fluent software. In CFD simulation that run in transient condition are known as unsteady Reynolds average Navier-Stokes equation. This is my parameter of the CFD modeling. The wind speed is 8 meters per second with free stream and transient condition. The turbine model in the rotating domain constantly rotate according to applicable tip speed ratio. Okay, next. This is my result. This is my model validation. The coefficient of power result in this study compared with the reference CP calculated from the investigation of Song et al. 2019 and the experimental CP from Castelli, Englaro, and Benini 2011. Maximum error or deviation in this study is, and previous study reached 5.04% with the average disparity of 1.05%, which can be said to be a good validation. This is my moment coefficient result. The value of Cm in one rotation of the rotor varies depending on the angle of attack experienced by rotor. In the variation of the addition HIV, the value of CM look greater when compared to variation without variation HIV under tip speed ratio 1.5 condition. The curve is of CM repeat every 120 degrees, which occur because the turbine has three blades. Okay, next. This is my power coefficient result. The power coefficient is in this study result from the average value of CM multiplied by TSR. The power coefficient of its geometry in the TSR range of 0.5 until 2.5. The variation of the addition of the turbine with the highest power coefficient result in the triangular HIV variation, which occur at TSR 2.5 with a CP value of 0.36. It can be seen that adding HV with trapezoidal and triangular geometry can delay flow separation, which is in this case occur at high TSR. This is my visualization of turbulent kinetic energy. The installation of the vortex generator turbine blade was also suggested by Kaufman, consistently increasing the transfer momentum from the outer area to near the boundary layer wall, and inducing an increase in turbulent kinetic energy. The next is my conclusion. My conclusion is high efficiency vortex can effectively increase the turbine's power coefficient and delay flow separation at relatively high tip speed ratio. The highest power coefficient in this study was achieved by the HV variation with triangular geometry at TSR 2.5 with a CP value of 0.36, where this value experienced an increase of 13% compared to the variation without HV. Visualization of the flow also show that variation in the addition of HV produce higher turbulent kinetic energy than variation without HV. Well,
thank you very much for your precise talk concerning content and concerning the time. To our deep regret, we have no time for a question, but I think our audience will touch you by chat. Thank you very much again.
Okay, thank you very much.
Felipa, may you assist in the
yes. Yes. So now we have the next talk that is with the title Plastic Strain Localization Mechanism in Aluminum Magnesium Alloys as a result of jump-wise processes in the defect structure of materials. And the first author is Mikhail Sokovivov. So please. Perfect, we see everything. Yeah, so you can start. We cannot hear you. I think you should unmute yourself. Still, we don't receive any audio from you. Can you try to unmute yourself? Yeah, still not working. Can you try to speak? No, we don't hear you. You should unmute yourself. No. Sokovico.
Non riesce a fare Sokovico. Allora, quella lista dice non c'è no.
Sokovico. I think are you able to reshare again and try to speak? Yeah, so I think we can probably go to the next one and keep this as the last presentation of this section.
Yes, of course. I can share my screen.
Yes. Perfect. So now we have the presentation with the title Modeling of the Fractal Behavior of 3D Printed Polymers using XFAM by Hakimi and Hakimi. So please.
It's clear?
Yes. Go ahead.
Thank you, Simon.
Thank you so much.
Good morning, everyone. I'm very pleased to present to you my work, Modeling of the Fractal Behavior of 3D Printed Polymers using XFAM methods, which is for me a worldly challenge and a great pleasure. So in this perspective, I will present the work according to the following plan. I will start by introduction, then our problematics, method and materials, then I will give you an overview of results and finishing by conclusion. As you know that 3D printers are a device that allow to create 3D dimensional objects. Materials such as using materials such as plastics or metal or wood. 3D printing are generally used a specific instruction called layer printing to create the object by adding successive layer until the object is completely created. So there are many types of 3D printing technologies, including the ones use thermoplastic and form wire, others use light colored resin, and others use power technologies. For our case, we are interested to thermoplastic and form wire, especially fused deposition modeling or fused filament fabrication, which based on heated filament in a extruder heat up to semi-liquid states. Those are the 3D printer in our laboratory and the material used for the study and its specifics. So the fused filament fabrication technique is basically using thermoplastic materials made on EBS or PLA or PA, pushing it into a heating block into a nozzle. The whole thing travels along predefined path, which already defined, for example, G code, and deposit the all material, so that the specimens being produced in layer by layer fashion. There are many types of head for printing, using, for example, using several printer head for multi-material, or special one for printing fiber reinforced materials. To get parts with high quality and high mechanical properties, there are many parameters to control, including the concepts model, the raw material, the filaments used for fabrication, the environmental factor, and also the build orientation. And finally, the process parameters, including the outer and the inner shell, the layer thickness, and the printing speed. As you know that the academic and the industrial research are attracted to this technology. And of course, this attention is made by its abilities to create objects with high complex geometries with low cost, except that they are meaning hardest thing to model the 3D printing. For example, considering the layer orientation. how we can model specimens considering the layer orientation, and also what should be the interaction between layers and what's its properties. We know that 3D printers are based on filaments, so how can follow and how can detect the crack propagation, and developing model that used to determine the crack propagation for 3D printer polymers. The first step in our process is to create 3D model using computer-aided design software based on specific dimension, which is mentioned in the figure. Then the CAD converted into standard additive manufacturing ASTL file, imported and digitally sliced using a slicing program. Its parameters shown in the table. The second stage required the transfer of the slide file into G-code. And third and last one is building the specimen layer by layer. During the printing, the nozzle milled the filaments and extrude them onto a building samples. Then we carry the tensile test using our machine, our laboratory MTS machine for tensile test. With the load cell of 30 kilonewton, the cross speed was 1 millimeter per minute, according to the standard used for tensile tests. A simulation was made using the same boundary condition, especially the layer orientation, and also for using to play for the first time, as it's shown in the right figure. And already said that it's hard to define the correct interaction between filaments, so that we define one which is similar, which is master-slave interaction with using hard contact properties. The shown figure presents a comparative study between the experimental and the simulation, as it showed that, as it showed the table in the right showed that the mechanical properties are similar. In other hand, the mechanical behavior presented in the curve are completely different. For this reason, the video presents the evolution of the crack length on function of time for the two layers, as we showed at the beginning. At the beginning, the crack speed is low, and I see that it's controllable. After 30 seconds, the crack behavior of the 3D printer specimen diverge and being uncontrollable, which is confirmed in the right graph. The crack growth is measured by seconds of successive image and frames calculation of the crack length, which based on the size of elements. For example, we have in the example we have 11 elements, which multiplied by the size of the element, which is 0.5 millimeters, which equal to 5.5 millimeters. That's it. That's because the calculation code does not have a direct method to calculate and to determine the evolution of the crack and function of time. Therefore, a various image was taken as measured. On the other hand, the experiment was recorded using a camera. So an adaptive study was made, fixing the starting and the ending of the experiments with the starting and the ending of the record video. Then we split the video with total length of 26 seconds to 38 frames. The conventional time for each frame was 0.7 seconds, and the deviation for each frame was 0.7 seconds. This deviation was obtained to study the crack length, and the crack length was studied using image G by importing each frame and selecting two reference points. One for the
sorry to interrupt you, but we need to conclude now. Thank you.
Yeah. I think that I didn't depass the time because I started. It's 80 minutes now.
Yes, but you can finish, of course.
Yeah, of course. By importing frames, selecting the two reference points, the starting and the ending. And it should mention that the program work according to ladder of 23.4. The two graph shows the evolution of the crack length in function of life fraction for the experimental sample test and the simulated one for each sequence of frame, as it's shown in the beginning that the crack appeared slowly, and after 0.7, the crack behavior increased rapidly and diverged to uncontrollable zone. Using both of the results, the experimental one and the simulated one, the left figures present a comparative study of the crack growth in function of life fraction. In other hand, the quick propagation of the crack is a result of the increasing of stress intensity factor. This increasing is plotted in the right figure, which describe the evolution of the stress intensity factor. The crack length as a function of the crack length, and the stress intensity factors are calculated by the empirical formula of Minerally in 1995, and the calculated stress intensity factor value seems identical, and the critical stress intensity factor seems that is about 5.65 MPa square meters. As you show that the curves seem similar. As a conclusion, we can say that the current study is not able yet to capture the mechanical behavior and the mechanical propagation of the crack. It should be beneficial for the future research to investigate this issue by considering the boundary condition and also the bonding condition between filaments and the layer. So to improve the model, we should import the real geometry of the structure, which is a program already developed that it's under testing, and also defining the correct interaction between filaments. And finally, use the digital image correlation technique to get more results to improve the experiments, and by importing displacement in calculated code. Thank you.
Thank you so much. So I think we don't have time for questions. Thank you so much for the nice presentation. I will call again the previous author. So the title of the presentation is again Plastic Strain Localization Mechanism in Aluminum Magnesium Alloys. And the presentation was by Michael Sokovikov, Sergei Uvarov, Mikhail Simonov, Vladimir Oborin. Is this author available for presentation now? If not, we can go to the next. No, yes, we are. Yeah, we can go with this presentation. So.
Okay, did you hear me?
Yes, yes, now yes.
I'm using the computer for Oleg Naimak for this.
Yeah,
sorry.
Try to be a bit quick because we lost a bit of time before.
Okay.
But
so my talk is about plastic strain localization. Actually, there are two approaches for explaining plastic strain localization under dynamic loading. Is a mechanism of thermoplastic softening or structure-induced softening. So we propose that main mechanism is structure-induced softening. Then it can be followed by thermoplastic instability. So we measure temperature is using of infrared camera. We have tested different types of specimen in order to choose most suitable for our case. First geometry is variation of head-shaped specimen. So in this modification, we can observe plastic localization from the edge of specimen. Another type, we tried to use special equipment to make a ideal share as in torsion Hopkinson bar, but we have problem with stability of specimen and with friction. Another type is inclined cylindrical specimen. We also can observe strain localization, but we have also problems with interpretation of results because of friction and so on. This is another type when we observe perforation of aluminum target with steel projectile. So we also observe rise of temperature, but not as high to induce thermal softening. And finally, from other experiments, we deduce some parameters of our material, and with using statistical model developed by Professor Neimark, we do numerical simulation of our experiment, and we choose modified head shaped specimen because we find that it is more suitable for our case. So we in our calculation we find stress concentration and temperature distribution, and calculated temperature distribution in our specimen is in satisfactory agreement with our experimental observation. Also, it was possible to measure strain field in our specimen with using DAC technique. And on the left image, there is a strain localization measured by DAC technique, digital image correlation. On the right, calculated. And magnified area on the low pair of pictures. So we also reached quite satisfactory agreement in calculated strain and measured strain. So, as a conclusion, with using infrared imaging technique, we have measured temperature during the strain localization and find that it is not, in our case, is not as high to provoke thermal softening. So we assume that we have deal with strain localization induced by structure evolution. We have done numerical simulation of our experiments, and the results of the numerical simulation is in satisfactory agreement with our experiments. And also, we found that modified head-shaped specimen is more suitable for this kind of experiments for investigations strain localization during the dynamic loading. So thank you for your attention.
Thank you so much. I think we don't have time for questions because we are 4 minutes late on the program. I will ask Professor Neymark to introduce the next speaker, so he can now chair until the end because we have finished his presentations. The next one is measurements of loads acting on electric bus in urban traffic. Yes.
Felipe, I am here.
Yes, yes, perfect. So you can go ahead from until now.
Okay.
From now to the end.
Okay. And because I was attracted to some administrative tools, I understand that now we have a presentation by
Bartolomei Valcatz.
Yes, that's me here. Can I start?
Okay, okay.
Yes, yes.
Thank you very much. We have now a presentation by Bartolomei, measurements of loading action on an electric bus in urban traffic. It's okay?
That's right.
Okay.
So, ladies and gentlemen, my name is Bartłomiej Walczak. I'm working in R&D department at Solaris Bus and Coach. I'm a PhD student at AGH University of Science and Technology in Poland. Today I'm going to speak about the measurements of load acting on electric bus in urban traffic, which I prepared together with my colleagues Piotr Malaca, Dariusz Michalak, and Wiesław Staszewski. First of all, aim and plan of the activities. In the bus industry, there are no generally available guidelines regarding fatigue calculation, for example, analogous to DIN EN 12663 from the railway industry, and the manufacturer must rely on his experience in selecting the appropriate loads for strength analysis. The aim of activities are the measurements of load acting on the electric bus in normal operation, which will help to improve the design process and allow safe optimization using state-of-the-art tools. To meet that goal, in the first step, pre-test finite element method simulation of the prototype structure was done, and key points of measurement were selected. Then the bus was instrumented and measurements of standard maneuvers and driving through obstacles were done. In the third step, test drives in urban area were measured. After this step, data was analyzed and sections with the highest influence of fatigue damage were selected. These sections were scanned for further numerical analysis. So the gathered data in the future will be used for the following works. First of all, definition of extreme load conditions, defining the fatigue cycles. Scanned roads will be used for advanced dynamic numerical analysis, and reference signals will be used for validation of numerical models. Now a few words about the measurement object. They were done on prototype bus visible on the above picture. It's almost 15-meter long 3-axle bus with traction motor power of 300 kilowatts and more than 620 kilowatt-hour of energy stored in the batteries. Gross vehicle weight is 26 tons, which assumes up to 65 seats and more than 100 passengers in total. On this slide, you can see why the electric bus is different than the diesel. So the main reason are the mass parameters of the elements assembled on the roof. In the standard diesel bus, only air conditioning unit is assembled on the roof, but in case of electric bus, total mass of roof elements exceeds 3 tons, including 3 traction batteries with cooling system, traction, electronics, pantograph, and braking resistor. In the lower part of the bus, additional 4 traction batteries with the weight of 2,400 kilograms are present. And finally, traction motors, which weight is only 260 kilograms, which seems to be low weight in comparison to diesel bus. It all gave us more than 5 tons of the powertrain elements. In the first step of the measurements of our works, finite element method analysis was done using SimCenter Nastran software. There were 4 made load cases of generic loads used as a pretest. It was emergency braking, cornering, driving through bump, and frame twists. On above picture, you can see stress envelope of that load cases, which the most loaded areas were chosen. As you can see in the table 3, it was chassis, a right wall, and the roof. Selected points for measurements. As you can see on exploded view of the structure, on the left side, there were assembled strain gauges. Most of them were located in the chassis. It was 21 measurement points, where the highest loads from the suspension of the powertrain and the powertrain are introduced. Sidewalls were investigated mainly in the door areas, and it was 7 points, and roof below the traction batteries, there were 2 tensometric points. Also, suspension components were instrumented, and there were 13 tensometric points located on the steering rod, stabilizers, and reaction rods. Additionally, there were 5 accelerometers on sprung mass, and the main goal of location, give me a second, the accelerometer here, is the collection of the accelerations of the body frame, which will be used in the further analysis to prepare fatigue assessment similar to DIN EN 12663 from railway industry. Others are used for observation of the local responses of the structure. Also, on each wheel hub, accelerometers was assembled, which signal in the future can be used for dynamic FE analysis. As a validation signal, so we used also wire linear displacement sensor, which were located near each air spring, and also in 3 sections of the structure, where we measured the diagonals displacement. All the tests were recorded by camera located in the windshield, and also signals of powertrain and tachograph were recorded via CAN network. First testing phase assumed scenarios like emergency braking, slalom, bump, bad quality road, railway crossing, and crossing the car. So the most loading for chassis were emergency braking and slalom. The highest registered forces in the suspension elements were registered for that 2 tests. What is shown on picture 7, we can see that there was extremely high force in the rods of the driving axle. And also bump test was causing highest response of the roof elements and sidewalls. In the highest part of the picture 7, you can see maximum magnitude of acceleration in loading direction. For braking, it was 6.6 meters per second square of deceleration. For slalom, the highest magnitude was -4 meters per second square in the y-axis. Together with local transportation company from Poznań, 3 city roads of varying difficulty were chosen. Together, it contains 79 sections of different quality of roads. Bus was tested in 2 configurations. First included only sitting passengers, and second fully loaded. And for the purpose of simplified fatigue analysis, as I mentioned, analogous to the one from the rail industry, acceleration sensor from bus interior was analyzed. To extract cycles such as braking and cornering, signal was filtered within the Butterworth filter for longitudinal and lateral axis, and it was reduced to 10, the boundary was 10 Hertz. For vertical axis, it was 20 Hertz. After that, it was processed with the rainflow counting algorithm, which extracted cycles. So for the purpose of fatigue simulation, this data need to be extrapolated for equivalent of 1 million kilometers. In the next step, influence of each road on fatigue strength was checked. For this purpose, based on strain gauge result, each strain gauge was processed with rainflow counting, and the accumulated damage was calculated using parallelogram minor law. On picture 10, you can see the results for representative bus areas, and road sections connected with the highest accumulated damage for each superstructure area was selected for scanning.
I'm sorry,
May
may I recall you about time, okay?
In the last step, selected roads were scanned using high accuracy kinematic LiDAR. Total length of scanned sections was about 10 kilometers. You can see here the scanned sections and conclusions. The measurements are to be the basis for more accurate strength analysis, which may allow responsible vehicle weight optimization. Data from the bus body acceleration are to be used for preparing the basic fatigue load cases. Scanned roads used with state-of-art software, nonlinear characteristics of the suspension and advanced tire model gives opportunity of realistic drive simulations. Further work will focus on numerical analysis and correlation with the test results. Also, a classification of scanned road qualities and its deeper analysis will be done. Thank you very much for attention.
Thank you very much for consistent talk. And since we are in the very tough schedule, could we attract audience to touch you directly for the question? Thank you very much again. We will go to the next presentation that will be given by Nur Suhata MD-Nor, the behavior of one hollow interlocking concrete block under flexural loading. Please. Are you okay?
Okay, can you see my slide?
Yes.
Okay, thank you. Okay, thank you, Session Chair. Hi, good day, everyone. My name is Suhada Makno from Civil Engineering Studies, College of Engineering, University Teknologi Mara, Penang Branch, Malaysia. Today, I would like to present the topic on the behavior of one hollow interlocking block. Okay, the behavior of one hollow interlocking block made from recycled concrete aggregate under flexural loading. Okay, this one is my presentation outlines. The first is motivation, and then objective, experimental program, results and discussion, and lastly is the conclusion. Okay, as we know, if you refer to this construction waste, most of the world's daily solid waste is attributed to the construction industry, with concrete waste making up a significant proportion of this waste. The construction waste increase every year and has a negative impact on the environment and causes social problems in the surrounding communities. And if you refer to this Malay Mail 2023, okay, based on this news, February 2023, this year, the construction waste is estimated to be about 27,068.4 tons, with concrete and aggregate waste accounting for the largest share of 17,820 tons, or 65.8% of the total construction waste generated. It is increasing every year as 326 tons of construction waste was disposed of in illegal dump site in Kuala Lumpur only, okay, which accounted for 94.6% of the total illegal waste generation of 344.3 tons in the city. Therefore, it is very important to manage and reduce the amount of construction waste generated by adopting sustainable waste management practices such as waste reduction, reuse, and recycling. Okay, so in this case, we prefer to reuse the material rather than we dispose to dump site, where the crushing of concrete waste from construction and demolition waste has proven be a successful method for obtaining recycled concrete aggregate. This recycled concrete aggregate can be used as a substitute for natural aggregate in the production of new concrete, resulting in the production of recycled concrete aggregate. From the review, found that the strength of the material or structure containing recycled concrete aggregate reduces as the percentage of recycled concrete aggregate increase. Although recycled concrete aggregate reduce strength, it still can be beneficial in other applications as the construction industry, as it is constantly looking for new and innovative ways to improve performance and application, such as in the production of interlocking concrete blocks for wall partition. As limited review found on the use of recycling concrete aggregate for production of interlocking concrete block, hence the study investigated the behavior of the interlocking concrete blocks made from recycled concrete aggregate and loaded with flexural loading. So this is the main objective of the study, to study the behavior of one hollow interlocking concrete block made from recycled concrete aggregate under flexural loading. Okay, this is the composition of the material, okay, which consists of water, cement, sand, natural fine aggregate, sand or natural fine aggregate, recycled concrete aggregate, and superplasticizer. In this case, we use water cement ratio about 0.65. The mixture of the concrete was based on ratio 1:4 for cement, 1 for cement, and 4 for aggregate. So in this case, the natural fine aggregate was 50% and recycled aggregate about 50%. And then we added 1% of superplasticizer based on cement weight. And this one is gradation of the recycled concrete aggregate and sand. And this is preparation of recycled concrete aggregate. In this study, the waste material was tested cube that we collect from batching plant, which has the same range or the same grade of concrete, 25 to 30 megapascal. So this is dimension of the interlocking concrete block with a size of 390 millimeter length, 100 millimeter width, and 100 millimeter thick. If you refer to this one, the width of the groove is 30 millimeter, and then for the tongue also 30 millimeter. And then depth of this groove 15 millimeter, length for this tongue is 15 millimeter, and this one hollow is scattered at center of this interlocking block. Okay, so this one 3D for solid interlocking concrete blocks, and this one 3D for one hollow interlocking concrete blocks. So after all ingredient has been thoroughly mixed, the fresh mortar was poured into the formwork and compact to remove a pocket. The fresh mortar was then left to set for 24 hours, and the formwork was then removed. The cubes and interlocking blocks were then cured for 7, 14, and 28 days in a curing tank filled with water. The samples were cured to keep the mortar moist and prevent cracking. Once the curing process was completed for a given age, for the specific age 7, 14, and 28 days, then the specimen were tested. This is the formwork for the production of interlocking concrete block, okay? And then this one, the concrete mix was poured into the formwork for production of one hollow. And this one is hardened one hollow interlocking block. This one hardened solid block, and this is production of solid blocks. Okay, this one is test setup of the interlocking concrete block. In this study, we put one LVDT or linear vertical displacement transducer at center of this interlocking block, and then the strain gauge was located at center at the other side of this interlocking block. So the effective length or span from support to another support is 270 millimeter, and this interlocking block has loaded with phase rate of 0.1 millimeter per minute. Okay, so numerical application using abacus for the static analysis of both solid and hollow concrete blocks. And then this one results and discussion. if you refer to this, this is result for compressive strength of cubes at 7 days, 14 days, and 28 days. We can see that the compressive strength of the cubes increase as the age increase. And then this one result for ultimate load and flexural strength of interlocking block for at 7, 14, and 28 days. This one graph for ultimate load versus age of interlocking block. From these figure tables and figure, we can conclude that we can summarize that the ultimate load increases with age, and then the ultimate load of the solid block is higher than that of the hollow block at all ages. The percentage difference at 28 days between a solid and one hollow interlocking block is 54%. And then this one result for flexural strength of interlocking block. So the flexural strength increase with age. We have similar finding for this flexural strength and versus age of interlocking block, where the strength of the solid block is higher than that of the hollow block at all ages. The strength of solid block is 5.33 Newton per square millimeter, and hollow block is 2.45 Newton per square millimeter at 28 days. Okay, why this happen? This is because the void in the middle of the block reduces the ultimate load and the strength of the block. This one is for why flexural strength for hollow block is lesser than solid block. The presence of voids, the presence of void in the hollow block reduces its overall stiffness and makes it more susceptible to bending under load. So this one is strain deflection relationship of interlocking block at 7, 14, and 28 days. So this one is maximum deflection, the maximum deflection. If you refer to this slide, you can see that the solid block has lesser maximum deflection compared to one hollow. For example, at 7 days for solid, the maximum deflection is 0.048 millimeter, and one hollow interlocking concrete block is 0.072 millimeter with a difference of 50 millimeter. And then at 14 days, okay, for solid is 0.097 millimeter. And then for one hollow is 0.142 millimeter. The difference at this age is 46%. And then the maximum deflection for solid at 28 days is 0.39 millimeter. One hollow interlocking block is 0.492 with the percentage difference of 26. Okay, so in this case, the interlocking block is higher than that of the solid interlocking block. This phenomenon indicates that the deflection, the maximum deflection, is due to the bending or sagging of the interlocking block under load, which is influenced by a variety of factors, okay, such as the material properties, geometry, and boundary condition of the blocks. Okay.
I am sorry, may I disturb you concerning time?
Okay, which is influenced the variety of factors such as the material properties, geometry, and boundary condition of the block. The main difference between solid and hollow blocks lies in the geometry. And then I move to the next slide. Wait, okay. Okay, this one result for strain deflection relationship of interlocking block at 7, 14, and 28 days. And we found out that the maximum strain is inconsistent with respect to age, and the maximum strain in one hollow interlocking block is lower than that in a solid block. And this one crack pattern and the simulation using Abacus model, where the crack pattern of the interlocking block observed visually match with the displacement contour in the Abacus model. This conclusion, the compressive strength of the cube made from 50% RCA and 50% sand increase as the cube age increased with the maximum strength of 34.54 megapascal at 28 days. And then the flexural strength of solid block and the hollow block with 50% RCA at 28 days is higher than that, higher than at 7 and 14 days. And then the deflection of one hollow interlocking block is higher than of solid block with difference of 28%. The maximum strain in hollow block is lower than solid block. And then the crack of the interlocking block, concrete block was found visually in the middle of the block and matched well with the displacement contour from the Abacus model. Thank you.
Thank you very much. Thank you very much. Talk is very interesting, but we have passed the time limit, and I think our audience will ask you directly. And Filippo, may you assist in the following talk? Okay.
Sorry, do you want I introduce the next one?
Yes, yes, please.
Okay, so the next one is combined application of point distribute fiber optic sensor for measuring gradient strain fields. And the first author is Grigori. Think you can share your screen?
No, nobody?
Nobody? If there is nobody,
I don't know.
No, I don't think so, because no one is replying. So we can go to the last presentation of this section, that is application of the limit design of design state to all Giarder ultimate strength evaluation of the ship shape structures. And the presenter is Aditya.
It will be presented by me, Imadin Faki.
Yes, you can go.
Okay, thank you.
You can share your screen and start. Thank you.
Okay, good morning, everyone. I'm Imadin Faki from Universitas 11 Maret. Will explain about application of the limit state design to Hall-Giller ultimate strength evaluation on the ship shape structure. Throughout 2022 and 20, there were 2,837 ship incidents on European Union flag vessels. To prevent incident during its service lifetime, it is necessary to consider the ability of the ship design to withstand operational loads, environmental conditions, and unexpected accidents. These variables are represented in limit state design. Based on Pike and Hayambali, the limit state consists of serviceability limit state, or SLS, ultimate limit state, or ULS, fatigue limit state, or FLS, and accidental limit state. During its service lifetime, a structure will experience degradation caused by various things. Pike describes several factors that have a major influence on structural degradation. This factor was geometric factors, material factors, the fabrication and melting process factors, the temperature factors, impact factors, human factors, degradation factors due to lifespan, and accident damage factors. Based on these factors, limit state design was divided into 4 categories. The first one was SLS, that represents the criteria for the structure's ability to support operational use needs. Next one was ULS, that represents failure that may occur in structures or components as a result of various loads on the structure. And the next one was FLS, that represents the accumulation of damage as the effect of repeated actions that can cause cracks in the structure. And the last one was ALS, that represents abnormal and unpredictable conditions. The partial safety factor is a method to obtain safety level of structure design by applying loads and resistance factors that represent the capacity of the design and design needs during service time. A design strength or capacity can be defined for a lower bound or 95% accident value, whereas a design load or demand can be defined for an upper bound or a 5% accident value, so that when depicted in the form of a graph, it will be as follows, where the probability of failure was located in the shape part. Based on that, the design capacity must not be lower than the demand for the safety factor to reach minimum value of 1.0. Partial safety factor can be calculated using equation 1. ULS, or ultimate limit state, is closely related to the loss of structural equilibrium, the achievement of the maximum resistance value of the structure, and the instability of the structure as a result of collapse of support member and plating. In ship-shape structure, failure of structure ideally occurs in ductile state. To achieve that, there is some factors that must be fulfilled. That is, mechanical properties or material must, especially toughness, must meet the requirements. Structural design and joints must allow plastic deformation to occur. Each member of structure must form an array that allows a decrease in the capacity of structure not to occur suddenly. And lastly, there are no initial imperfections in the structure that can trigger structural failure. As can be seen in the chart, ULS can be simplified by basing the ULS value on the ultimate strength derived from the buckling strength of each member. To facilitate the calculation of ULS, in ship-shape structure unit hulls under vertical bending moments, the ULS calculation may be expressed as equation 2, where the partial safety factor for each bending moment were described differently between each type of ship hull. And based on IGF27, the calculation of still water and wave-induced bending moment was divided into two categories. These categories was based on the condition of ship hull when affected by ocean wave, that is, hogging condition and sinking condition. As stated in IGF27, the still water and wave-induced bending moment was described as equation 3 to 6. HUF, or Hull-Gider ultimate strength, in ship-shape structure, failure is controlled by buckling, ultimate strength, and yielding of longitudinal structural elements. Hull-Gider ultimate strength is a method to calculate the ultimate strength of ship-shape structure by cutting the center of the ship hull transversely and simplifying it as shown in the far right image. There are various methods for determining HUS that have been developed so far through history. The first one was done by Caldwell, whose formula to calculate HUS but didn't consider the reduction in the strength of each element. Weda and Rasset formulate ideal structure unit methods, or ISUM, to lower the degree of freedom and nodes in the system structure, when the structure was divided into the biggest possible structural units, whose geometric factor and material nonlinear behavior can be idealized and described in a concise analytical numerical form. One method that is quite well known is Smith methods, whose simplified beam column methods taking into account the elastoplastic behavior of panels and local buckling. Based on Smith methods, IGSR simplifies the incremental iterative methods for evaluating HUS. Using analytically derived stress strain curve, the incremental was increased in each step and could be defined as Xn as formulated in equation 7. In the calculation of HUS using Smith's method, Hull-Gider was divided into several parts. These parts are categorized into stiffener elements, stiffener plate elements, and the last one was hard corner elements. Each of these categories was taken into account separately following the increase in curvature value. And the calculation of each of these categories was as formulated through equation X213, where each element has their own effect on ultimate strength value at each increment. So the calculation of each component must be calculated accurately and separately. The accuracy of ULS calculation is greatly influenced by the accuracy of Hull-Gider ultimate strength calculation. Pike stated that the more complex the HUS calculations, the more accurate the calculation results will be. Several studies have been conducted to improve the accuracy of HUS calculations. Some of them are by using non-uniform uniaxial truss as the main loads instead of uniform truss as used in IRCSR. It is based on the representative element from neutral axis, the more aforementioned ratio depart from unity. In addition, the influence of initial imperfections due to the effect of assembly plates is also considered. It is based that during the assembly process of an iron structure will undergo initial imperfection as an effect of welding, where the initial imperfection here in welded metal structures include initial distortion, residual stress, and softening in the weld fusion zone. Also, throughout its surface lifetime, the plate thickness was reduced as the effect of corrosions. The corrosion of ship structure will linearly and uniformly reduce the thickness of structural components based on its component location. According to Igida et al. At 2001, that examined the structural features of 11 single hull tankers that had average level of corrosion, the section's modulus drop was less than 15% of the original value. In addition to adding variables, combining methods can also improve the accuracy of HUS calculation results. Olmes and Bilateral et al. In 2015 proposing new methods that was composed from ISUM based component discretization and Smith methods based progressive collapse analysis, and conclude that these methods was adequately reliable to estimate Hall-Girdle ultimate bending moment. At least it can be concluded that limit state design calculation are mandatory methods that need to be passed through the design process. The 4 steps of limit state design represent every condition that may occur in the ship structure during service lifetime. The method to determine the ultimate strength in ship structure is to determine the Hall-Girdle of the overall structure. And lastly, HUS calculation can be improved in accuracy by adding variables that occur on the ship throughout its service lifetime, or combining several calculation methods. That's all from me. Thank you very much.
Thank you so much for the nice presentation. And now I think we are perfectly on time to conclude this section. I want also to thank Professor Oleg Neymark for being co-chair of this section. And straight away,
thank you very much for all our participants. I think all presentations were interesting and consistent. And to our, I think, common deep regret, we have not enough time for discussion and questions. But I think communication could be provided in the following. And due to the presentations that were made. Thank you very much, Filippo, for your friend assistance.
Thank you so much to you for your kind support. And now I will leave the floor to Costanzo Bellini, who is the chair of the next section.
All the best for all.
Good morning, everyone. I'm Costanzo Bellini from the University of Cassino in Southern Lazio, and I will chair this section. We can start with the first presentation, that is investigation moisture content effect on bearing capacity potential failure of strip footing rested on silty sand soil based on crack characteristics and assessment using non-destructive test. The presenter, the first author is Nurul Najia Binti Imam Robit.
Okay, hi.
Okay.
And good morning. I'm Mashita. So today I'm going to present my untitled investigation moisture content effect on bearing capacity failure of strip footing rested on silty sand soil based on crack characteristic assessment using non-destructive tests. So I'm from Center for Civil Engineering Studies, UiTM, Pulau Pinang, Malaysia. So this is on about how we can estimate or what we can determine the crack formations due to the soil bearing capacity failure. As what we know that the footing or foundations is a very important substructure below that carry loadings from the tops. So if you have a very weak soil, it can cause to the crack formation, for example. That's what I am saying here. So the structural stability mostly relies on soil foundation from carrying and transferring load to the layer or stratum of rock or soil. So the structural damage is significantly caused by differential settlement underneath the foundations and the structure and triggering to crack formations on the structure. So furthermore, the presence of structural crack can be due to moisture content variation. As what we know, the environmental condition as well as the load and also the soil properties are the parameters control to the formations of the crack itself. So what is the bearing capacity? The bearing capacity of soil is ability of the soil to support loads without fail in shear resulting to excessive deformation or settlement. So the effect of moisture content variation in dry and wet conditions for fully saturated, for example, degree of saturation is 100% or 0%, and unsaturated soil for degrees of saturation equal to 0 on the properties of the ground and the whole building, causing to soil deformation and differential settlement, which is mostly neglected in assessing the structural lifespan performance. So thus, in order to calculate the ultimate bearing capacity, incorporate the changes of moisture content and degree of saturations under the suction effect for unsaturated and saturated soil condition, as can be seen in these equations. So the equations originally from the Tzagi assumptions for saturated soil. So it is adopted as well the Moore column failure envelope. So in order to calculate the bearing capacity for different moisture content on top of it has the saturated conditions and also unsaturated condition of soil. So this formula is more reliable and applicable in order to estimate the bearing capacity of the soil, which carrying the superstructure loadings. So this study aims to investigate effect of moisture content variations on bearing capacity of street footing on silty sand based on non-destructive test data informations. So the visual inspection was carried out and structural assessment of the building, such as location, width of the crack, the length, the pattern, and the condition of the crack were recorded in order to classify the severity of the cracks. A non-destructive test, for example, here we will conduct on the rebound hammer test to determine the compressive strength of the concrete for the affected crack area. So in order to have some information from the soil, so the geotechnical properties will also carry out on certain testing, for example, moisture content, the compaction characteristic, as well as the shear strength of the soil, according to the standards what we had in the lab. So in order to have some impact from the crack formations on the building itself. So the next one carry out on the numerical study for the bearing capacity failure of street foundation with a 2-meter width resting on the ground surface by using the geotechnical finding element software Praxis 3D. So all these informations from the non-destructive test as well as the geotechnical tests were included in the numerical study. So the case area was selected in Penang, Malaysia, and you can see that this is the map for indicating the locations of the study area. So for the structural integrity by using the numerical study, so on the right side were tables for silty sands and also the footing. So you can see that the properties of soil and also the structures are important in order to have the analysis of the bearing failure. So in order to include the effect of the moisture content at this time, you can see that there are two values for unsaturated unit weight of the soil and also saturated unit weight of the soil. So below the ferrity level or below the groundwater table, so we're going to adopt unsaturated unit weight of the soil, and above we can adopt for unsaturated unit weight of the soil. So these are very important when you estimated the bearing capacity of the soil with different conditions of the temperature effect. For example, here we consider the moisture content during the dry and wet seasons. So from the result and from the result itself, through the visual crack assessment and as well as the rebound hammer test, for this point 1, it was considered as severe due to extremely huge crack width. So by refer to the Berlin scale, the approximate crack width of 15 to 25 millimeter was recorded, and it was considered as a severe damage. So this crack line was formed in a straight line about 3 meters upwards. So the pattern of crack shows that it cannot be considered as a non-structural damage. So on the right side is indicated tables that we have found on the crack assessment, for example, rebound number, and then the compressive strength of the concrete, the crack width, crack length, and also the crack damage category. So by conducting the geotechnical test, these are the tables, these are the parameters indicate in this table, mention that the soil type is a sand, silty sand, and the compositions of the soil itself for the sample, which has a percentage of sand, percentage of silt, and also clay, and the compaction characteristics indicate that the optimum moisture content is 17.05%, and also the maximum dry density is 1.83. So after we have this value of unconfined compressive strength, the stiffness of the soil can be estimated by using one equation established from the past study. So on part of the numerical study, for variations of the moisture content effect, by considering the degree of saturations at wet condition and also for the dry condition, as well as the degree of saturation from the 0.1% to the last 0.9%, as can be seen in this graph. And it shows that the higher degree of saturations and also the increase of the moisture content that will be increasing in the pore pressure resulted to the bearing capacity reduced. So these images indicates that the bearing capacity failure of the bear pressure below the footing itself, carrying 200 kilopascal loadings, indicating that the shallow footing has different bear shape patterns that indicate for different degree of saturation, 0%, 100% is a fully saturated, and the 50% for unsaturated conditions of the soil. So again, the effect of moisture content in the numerical study was assigned through the flow boundary conditions in this program or in this software. So a part of the conclusion that we have been made from this study is that the point 1 has experienced severe crack damage with crack with 25 millimeter, and the crack length is 3 meter. And this crack line was formed in the straight line about 3 meter upwards and considered non-structural damage. And from the geotechnical test, it is concluded that the sample is classified as silty sand, which we control the strength of the soil resulted to the bearing capacity failure. So the bearing capacity failure of soil from total displacement beneath the footing shows as moisture content and degree of saturation increase, the total displacement also increase. So this is due to the increase in the pore pressure and decrease in the shear strength of the soil. So that's end from me, and thank you for listening.
Thank you so much. I'm sorry, but we have no time for question. So we can skip to the next presentation. The next one is experimental and numerical study of the behavior of an aluminium, magnesium, manganese, aluminium alloy under different strain rates and temperatures. The first author is Aziz Kouas. Other authors?
Hi everyone. Hi. Donc, I present this work in place of Aziz Kouas, not present for family circumstance. Donc, I am Marzak Zarouki, donc doctor in mechanical engineering of the University of Tizi in Algeria. Is my first time in English. I will try present firstly. Donc, I have the pleasure to participate in this important event to present our work titled Experimental Study and Numerical Study of the Behavior of Aluminium Alloy under different strength rates and temperature. To carry out this presentation, we have chosen the following work outline. Firstly, we start with introduction. Secondly, we present the experimental part. Thirdly, we talk about the modeling and numerical simulation. Fourthly, we compare the numerical and the experimental results. And finally, a conclusion and a perspective. In this work, we study the effect of strain rate and temperature of behavior on aluminum alloy. To characterize this material, constant tests were carried out to plane sample cut in three directions of rolling. 3 directions, 0 degrees, 45, and 90. Then the behavior of this material is studied at different strength, height, and temperature. In terms of numerical modeling, the physical model of the GTM is extended to take account of orthotropic and the thermic and the viscoplastic behavior of these materials. This model was implemented in a bucket explicit using the ViewMat subroutine. The material studied is the form of the cold rolled sheet with a thickness of 5 millimeters. This chemical composition is shown in table 1. Table 2 and table 3 present respectively the mechanical properties and the lacquer condition. In the right of this slide, we show dimension of tonsil test specimen in case of 25 degrees and 290 degrees. We also show a traction machine and the thermal chamber with it. This slide gives the result obtained at different deformation rate and temperature. Donc, the result show that the material behavior is influenced by the strain rate and the temperature according to 3 direction ruling. The GTM model extended to account the viscoplasticity and anisotropy. Donc, we use the Hill criterion, and for viscoplasticity, we modified the constant H. The model has been implemented in the bucket explicit. The calculation using the flow chart, the following flow chart. The Arabas method is used to solve the model equation. This figure shows the tip of the mesh, C3D with 8R, and the boundary condition imposed with the material. The specimen is fixed in the loading direction, and the strain rate is imposed on the other side. The following figure shows the comparison between the stress strain curve and the contour of the homizet in the case of temperature 25 and the strain rate of 1 millimeter per minute in different ruling direction. This comparison demonstrates that the GTN extended GTN model successfully predicted the behavior of a material. The following figure shows the comparison between the stress strain curve and the contour of homizet in the case of a temperature 25 and the strain rate of 10 millimeters per minute in different ruling direction. The comparison shows that the extended GTN model accurately predicts the behavior of the material. Finally, this study helped you to conclude the following points. The studied sheet is anisotropic. The strain rate and temperature affect the behavior of the material study. The implemented model correctly reproduces the behavior of the studied material at different rates. The implemented model correctly reproduces the anisotropic behavior of the material. For future prospects, extend the GTM model to account the temperature and the height strain. The coupling with the temperature effect is under development. Thank you for your listening. I think that is firstly.
Thank you so much. Now we have time for questions from the audience. If there is any question from the audience. If not, I have curiosity, and can this approach applied also to other kind of material, not only metals, but also polymers maybe not, but to other materials in general, or polymers but at low temperature.
Yes. Hi. Hi. I don't listen. Hello. Hello.
Can you hear me?
Please repeat the question, please.
Yes. Can this approach be applied also for other materials, metal materials, or also polymeric one, but obviously at lower temperature for this latter case?
I don't know this, but I work in metallic only, on metallic material only. I don't think that be applied with the polymeric material.
And to other metals, for other metals, there are no problem, I suppose.
Yes, this model is applied for the steel. The steel, no problem.
Okay.
Steel, no problem. Thank you.
Okay, thank you.
Yeah, very much. Thank you. Bye.
So we can go to the next presentation. That is a numerical study for the first phase of the Milia solar well plant in Oman. The presenter is Amani Majed.
Hi, good morning. Nice to meet you, everyone. I will share my screen now. It is clear?
Yes.
Okay. My paper title is a numerical study for the first phase for Mira solar well plant in Oman. The outline of my paper, the abstract, solar stream generator model, system for phase 1, methodology and result. Abstract, offshore oil and gas production utilize several renewable energy techniques to meet its energy need and to enhance oil recovery, EOR. Using renewable energy can reduce fuel consumption and maintenance costs in upstream operation, in addition to reducing noise emission and improving safety. Renewable energy can also reduce pollution. As an alternative to natural gas, solar thermal enhanced oil recovery utilize concentrated solar power, CSP. Okay, for the Mira project in Amal field in Oman, solar energy was used to generate steam. 10% for total steam are produced during phase 1 of the project. This study presents a computational simulation for phase 1 Mira project only, where the amount of the heat required to convert 100 gallons of cold water to the at 450 degree Fahrenheit and 414.7 psi was calculated. According to the result, the steam injection per hour is 637 tons and with a percentage of error 3.46. Okay, the construction of Mira project. Actually, the Mira project in Amal field consists of 3 phases. Here, we just deal with the phase 1 of this process. The phase 1 can contribute 10% of the total output for this project. The total output is 6,000 tons. So in phase 1, the progress of the phase 1 is consists of 4 blocks. Each block consists of 5 to 4 loops, and each loops contain 8 rows. We can see here, this is a block from NELST 2018, consists of 4 blocks, and each blocks we can see here for block 1. This is a 5 loops for block 1, and each loop contain 8 rows as we can see here. We must understand what is steam injection. Firstly, the steam injection process is heating the reservoir by generating the steam at the surface or sometimes inside the downhole to convert oil from heavy oil to light one. The higher the temperature, that means the lower the viscosity of the oil. Thus, the heavy oil or I mean with a very high API oil with high viscosity oil turns into light one with a low viscosity, so that the oil mobility will be improved and improve the efficiency of the sweep. This is one picture from the Mira project. This is actual picture I took from internet to explain the whole process that Mira project use. Here we can see that we have a solar collector, which is the type of the solar collector parabolic trough one, can be seen in the greenhouse. And then they used parabolic trough collector to convert cold water to steam, and then the steam or the output steam will be injected in the heavy oil reservoir and then produce oil. The calculation, I didn't write all calculation here, but all calculation are used in my paper actually. Here we can see that the calculation or the main important angle that deal with the solar part to understand how can calculate direct normal radiation. Here the solar declination can be given in equation 1, our angle can be given into equation 2, and the most important equation, which is equation 5, that calculate the direct normal radiation. The direct normal radiation contains of two constant A and B that is taken from Esri and the sine of beta. The sine of beta can be written here in equation 6. We can firstly understand what happened inside the parabolic trough collector. This is a parabolic trough collector, and we can see that will be used to focus the sunlight on the pipe. Here we have a pipe. The pipe content of absorber pipe, which is direct contact to the fluid, which is here in Mira project is a cold water, and then this covered by the glass one. The whole process of heat transfer can be seen in the picture on the left hand side. Here we can see that there is an absorber heat that is absorbed from the sun and that pass the glass cover and then absorbed to the absorber, and we can see that we have inside absorber and outside absorber, and we can see also we have inside for the glass pipe and outside of the glass pipe. Solar radiation absorption, I calculated in this project or in this paper, the absorption of the absorber, which is, I give it at 1 and 2 for inside and outside, and also the equation of, or the heat that absorbed by the glass envelope. The result, firstly, we need to feed the program by some important data like maximum and minimum temperature whole the year. We have here whole year for the 27 and the wind speed also. After that, I used the MATLAB to calculate the direct normal radiation and its component. I mean by its component that the direct normal radiation in this project directed one single phase, just single phase, that the rotation of the parabolic trough collector is just in one phase, that is follow the direction of the sun, so that the value of the radiation that used actually in this project is the line 2 part here, as we can see. This is the direction normal radiation and its component for whole the year in 2017, January, February, March, April, May, June, and whole the year for 2017, which is the year of the producer and Mira project. Also, we can see here the absorption from the absorber and from the glass envelope for the inside and outside. We can see here this is for absorber, the up lines is for the absorber inside and outside, and the lower one for the glass envelope. Also this for whole the year 2017, March, April, May, June, and July, August, September. October, November, and December. After that, after we calculate the absorber heat that be transferred to the fluid in the parabolic trough collector, then we need to calculate the amount of the steam that produced from this process. Here we have 3 steps. The first step that deal with them would calculate the amount of the heat that used to heat the water from cold water to the heat water, and then to the vaporization, or the amount of heat that used to convert the whole steam at its boiling point. And then the last one, by using nomograph, we can calculate the amount of the steam that injected to the heavy oil reservoir. Actually, according to my calculation, I can find that the total steam injection per hour is equal to 637 tons, while the actual value from MIRA project is 660 tons, and with a very little percentage of error, which is equal to 3.47 actually percent. And this is I can say that this is can be used, this paper, to make this calculation for any project like a MIRA project. And the aim of this project at least is to use the solar energy to produce heavy oil. As I can say in the beginning, the heavy oil with a high velocity can be lighted by using steam injection. This is all what I have. Thank you very much.
You. Are there questions from the audience?
What?
Can you hear me?
Yes.
Okay. So no questions from the audience, and no time. We are a bit late, so we can go to the next presentation. Thank you.
Thank you. Thank you.
And the next presentation is optimized linear regression to compute the wellpool parameters. The authors is Mohamed Lamin Moussaoui. Is Mohamed with us?
Hello, Chairman.
Hello?
I'm looking for the file
okay.
on my computer. How to reach it? I have not found it.
You have shared your screen?
How to share a file?
Yes, but we can see your screen, your email box.
Huh? I can't find it. Partager l'écran. Where to find it? The computer. My project. Streaming. Écran. Files. Fichier. I have not found the computer on board. How to find the file? Open it. Okay. Conference. I have found it, and share.
You can share. Okay, you can share your screen.
I haven't found the menu. Of the conference. Where is this one? conference is I have not found the menu of the conference. Uh, 66. I have not found the menu of the conference. The conference is activated. Ah, okay. Now share the file. It is here. Okay. Share. My presentation is entitled Optimized Linear Regression to Compute the Variable Parameters. I am Mohamed Lamin Moussaoui from University of Sciences and Technology, Houari Boumediene, Algeria. An efficient, as an abstract, an efficient novel formulation for the computation of the beta and eta variable parameters is introduced in this work. This procedure consists to numerically optimize the errors between the data values shown in figure 1 and the corresponding regression function values using the least squares method to fit these data. A numerical example is presented to compare the obtained results and their efficiency in precision and computing time. Here we show in this figure the data, and these data values are plotted on the variable logarithmic paper, as it is seated in this reference one by a linear curve. And this straight line gives the value of eta, which is equal to 60 on the eta axis, and a parallel curve gives the value of beta equal 3. The curve is plotted from the origin 0. This is the graphic method. The variable method is by the probabilistic variable law, which is very suitable to fit arbitrary statistical data obtained in general from performed computations. For a random variable t, which is distributed with the variable law, we give the form of f of t function, where beta is the shape parameter, gamma the position parameter, and eta the scale parameter for this PDF probability density function. Here in the following figure, we show typical variable density functions where we have several forms which can be obtained experimentally or numerically. We have the left shifted distribution, or right shifted distribution, or centered distribution. And in the literature and the bibliography, we can show several distributions to represent a signal spectrum for a periodic signal spectrum, which is arbitrarily shaped. You have here PDF probability density functions in the right side, which gives the peaks of the periodic signal. Can have a periodic signal with a period t, and the scaled curves correspond to the signal, and we have here various values of n number of standard deviations, which are scaled from the variance and the variable x. Parametering on the Weibull logarithmic paper, we use here the linearization form given in reference to y equal beta dot x plus c, where these components are given here. The parameters beta and eta have always been obtained by the graphical method, as we have seen in figure 1 on the Weibull logarithmic paper. This method is tedious, and the obtained data can generate a nonlinear curve in some cases, which needs to be difficultly adjusted to get a linear curve. The optimized Weibull process in this analysis is given as follows. Based on the square total error minimization, where the optimization model is defined with the utility objective function u of epsilon and the variables of decision epsilon in the vector, in this vector, and epsilon is defined by the difference between the data values and the statistical data values and the linear regression approximation of these values, given with the constants r and functions phi I. The objective function becomes u of r, where r are the new generalized variables which has to be found, which are searched. The transformation gives the following approximation, following system of equations to be solved. This system of equations is obtained from the gradient of the function, and one has to solve a dot r equal b, where a is a matrix and r is the vector of the constants, and which form the approximation, and b is second second term vector. The Weibull probabilistic law parameters can then be efficiently computed with beta equal R2 and eta equal exponential minus R1 over beta. We have here a numerical example. The data cited in figure 1 are in the table 1, and the corresponding values are in table 2. And solving the linear system of equations gives the expression of the constants, which forms the which form the linear function. We can give here a comparison between these two methods. In the present method, in this analysis, gives beta equal 2.977 and eta equal 59.902. And the graphical method has given 3 and 60. We can show in this analysis that the computed parameters with this numerical process are closer to those obtained from the data values on the variable plot on the logarithmic paper. The comparison is this numerical method takes some seconds to compute the searched variable parameters, and the graphical method takes several hours when the data values are complicated, which need some transformations. The conclusion is we have in this analysis performed the development of an efficient numerical method to determine the variable parameters. And this analysis allowed to save more time with respect to the graphical representation, which needs a costly meticulous representation. The minimized errors between the nonlinear regression model and this numerical process and the existing data values allowed to obtain the optimal coefficients corresponding to the optimal errors. Thank you for your attention.
Thank you for your presentation. And as we have no time for questions, we have to skip to the next presenter. Thank you once again. The next presentation is entitled Simulation of the Flow in a Fractured Rock. The first author is Ahmed Al-Mukhtar. Is with us, or another author of this work. The work is Simulation of the Flow in a Fractured Rock. Authors Ahmed Al-Mukhtar, E. Goma, Ha. Arafat, and Mohamed Mzul. No one is with us. So I have to skip to the next one. That is effects of printing parameters on the fractured toughness of 3D printed polymer parts. The authors are Mohamed Reza Khosharavani and Tamara Reinike.
Yes, hello everybody. Can you hear me?
Okay, can hear you.
Okay, let me to share my screen.
Yes.
Okay. I would like to talk about our investigation on the fracture of 3D printed parts. Our research is entitled Effect of 3D Printing Parameters on the Fracture Toughness of Printed Polymer Parts. This research has been performed in the Institute of Product Development at the University of Siegen in Germany. This presentation includes introduction, which covers a brief definition of additive manufacturing and overview of 3D printing methods, their advantages and applications. In addition, material extrusion technique would be explained, and I will continue by experimental test where I will describe a specimen preparation and mechanical experiments, the obtained results, and finally conclusion. Manufacturing processes are the steps through which the raw material are transformed into the final product, and the manufacturing process begins with the product design and material specification from which the product is made. Over the years, different manufacturing processes have been introduced. One of the manufacturing techniques which was introduced in the last century is additive manufacturing, and it's known as a three-dimensional printing. American Society for Testing and Materials and also International Organization define 3D printing as a process of joining material to fabricate parts from a 3D model data. As you can see in this slide, they classify 3D printing into 7 techniques, which are binder jetting, material extrusion, direct energy deposition, material jetting, sheet lamination, powder bed fusion, and vat photopolymerization. These techniques are suitable for different types of materials. Here, some main advantages of additive manufacturing are listed based on the utilized technology. 3D printing is a fast process which have a positive impact on the environment. Moreover, in different 3D printing technique, multiple material can be used in one component, which is an advantage compared to the other manufacturing techniques, and high accuracy and reduction in the material usage are also benefits of 3D printing technology. Manufacturing techniques are covered different domains such as mechanical engineering, electronic, nanotechnology, and construction at different scales. Due to the benefits of 3D printing, this manufacturing process has been used in different fields such as electronic, medicine, aerospace, and automotive industry. It should be noted that 3D printing techniques deal with different material like metal, ceramic, polymer, and composites. As already mentioned, material extrusion is one of the main methods of 3D printing technology. Fused deposition modeling, or FDM, is example of material extrusion technology, and in the FDM process, the melt extrusion method is used to deposit filaments of thermal plastic according to a specific pattern. In this figure, a schematic of 3D printing based on the FDM process is illustrated. Let's go to the next section, which is experimental tests. In the FDM process, different printing parameters can be changed. For instance, printing speed, layer thickness, and air gap can be defined with the desired values. However, it is often difficult to control all of these parameters together, so it is important to investigate and determine the effect of these printing parameters on the performance of the 3D printed parts. In preparation of the specimen, a standard was used, and we printed dog-bone specimen based on the standard, and schematic of the dog-bone specimen and relevant details are presented in this slide. In this study, we used PLA material, and specimen were printed with different raster direction. You can see some details in this slide. A specimen printed in ±45 degree and 0 and 90 degree. And in fact, for the compact tension, we prepared the specimen according to the ASTM standard. By the definition, raster direction is a printing direction relative to the loading direction. Therefore, 0 degree refer to the specimen which are loaded in the printing direction. As a second variable, we printed the specimen under 2 different speeds, 20 millimeter per second and 80 millimeter per second. And we will show what is influence of these printing parameters on the performance of the parts. After printing process, we have conducted tests on the both dog bone samples and compact tension specimen. For the test on the dumbbell-shaped specimen, we use a hydraulic tensile test machine, which was equipped with a 15 kilonewton load cell, and the tests were performed at the crosshead speed of 5 millimeter per minute according to the relevant standard at the room conditions. Later, we did also compact tension on the printed specimen. Our tests were performed with the crosshead speed of 10 millimeter per minute at room temperature, and in this figure, a compact tension specimen after fracture is illustrated. In this slide, figure 7 shows two fractured specimens with different raster orientation. As it is depicted, crack growth is occurred parallel to the initial crack. As a result of the compact tension test, force displacement curve of different specimens are illustrated here. Based on the obtained result, printing with the higher speed has led to a decrease in the failure load. Moreover, specimens printed at the plus minus 45 degrees showed the highest failure load. The lowest failure load was belong to the 90-degree specimen printed at the highest speed. As a conclusion, I would like to review this presentation briefly. First of all, I describe manufacturing process and focus on the additive manufacturing. Also, I mention application of 3D printing and some advantage of this manufacturing process. In the second section, details of specimen preparation was presented. In description of experimental test, detail of compact tension test are explained. As a result, I describe effect of printing speed and raster direction on the fracture of the examined components. Thank you for your kind attention.
Thank you. Are there questions from the audience? No. So as we are a bit late, I come back to call. Thank you, Mohamed.
Welcome.
I come back to the previous presentation that was absent. Simulation of the flow in a fractured rock. Is one of the authors with us? The authors are Ahmed Al-Mukhtar, Goma, Arafat, and Nzul. Is one of them with us? No. So we can go to the seventh presentation of this slot, that is UHP FRC under impact loading. The authors are Nicoletta Tesio, Ezio Cadoni, Matteo Dotta, Daniele Forni, and Gianmarco Riganti. Is
yes.
one?
I'm Ezio Cadoni.
Okay. Good morning. The stage is yours.
Okay, thank you. Okay, you can see the presentation?
Yes.
Okay. Ultra high performance fiber reinforced concrete is an advanced cementitious material that combines high strength and toughness and high durability. These outstanding characteristics make this material a very attractive choice, and it is frequently used for a variety of structural applications, including bridge, high-rise building, and other special constructions. These structures might be subject to high dynamic loading, such as impact and blast. Engineering application of UHPC include protective structure and critical infrastructure. So like this phenomena. In the frame of a multi-year research project named protection of infrastructure elements from the effects of improvised explosive device and blast charges, that is supported by Alma Swiss Science and Technology of the Swiss Federal Department for Defense, Civil Protection and Sport, we have carried out an extensive numerical and experimental researches, and this research was subdivided in three parts: the material characterization, developed at the Dynamat laboratory, numerical simulation of UHPC plates under blast loading, and the blast test of these UHPC plates carried out at the Ondrik Detonic Laboratory near Spitz in the German-speaking part of Switzerland. The research was aimed to study the retrofitting system using ultra-high fiber reinforced concrete, and different sandwich plates were tested dynamically using C4 charges in contact and standoff distance of 3 and 6 centimeters. The mechanical characterization at a high strain rate was performed in different loading modes, such as the direct tensile test, the compression, indirect tensile test, shear, using sample having different shape, size, notches, and so on. We have analyzed several commercial UHPC having different fiber contents with different aspect ratio of high carbon striped fiber. And I'm going to present you some results on the high strain rate behavior of UHP-FRC in compression. To perform this study has been used a new apparatus designed to analyze the triaxial behavior of quasi-brittle material, such as rocks and concrete, under dynamic loading. This machine is currently under construction and was partially funded by the Swiss National Scientific Fund. It consists of 3 pairs of bars in 3 perpendicular directions and a pulse generator that is a pretension bar in this position. The pretension bar is pulled by means of an hydraulic actuator of 4 meganewton, and the brittle bolt that is placed in between that with this its raptor activate the test. The input bar is the solid continuation of the input, the pretension bar, and the other 5 bars can be considered as the output bars, and each one is at the end of these 5 bars there is other 5 hydraulic actuator that permits to impose the triaxial state. All the bars are instrumented with the string gauge in order to record the wave propagation in the system. The results I'm presenting you were obtained by using only the monoaxial configuration, the actual configuration, this is one, where the specimen is pre-strained before the dynamic test. The imposed pre-strain were 1 2/3 of the quasi-static strength. Dynamic tests were carried out at the same velocity by imposing 500 kilonewton in the pretensional bar, giving a stress rate of 1.6 terapascal per second. This is the graph in which you can see the evolution of the cracking process, and this is the response of the UHPC and HPFRC with different preloading in terms of stress versus time curve. All the tests have the same gradient up to the first 60 microsecond. Afterward, the stress versus time curve changes due to the presence of activated crack during the preloading process. Activated cracks and the stress rate play a crucial role in enucleating the cracking process that results in spaceman failure. The material had a more uniform response in tests with higher static loading values, but its strength was lower caused by the quasi-static loading in case of UHPC, while in the fiber-reinforced material do not present significant differences. In the next two slides, I'm presenting the results of the two materials with the same preloading conditions. This is the results for the matrix, the UHPC, in which this is the evolution of crack. And this is for, come on, this is an example of fiber-reinforced material. In this slide, I've shown the comparison between the two material, matrix and fiber reinforced one, in terms of experimental stress time curves. The peak load seems not be influenced by the presence of the fiber, while the post-peak is governed by the fiber content, and this influence decrease with increasing the spaceman length. We have observed that by increasing the stress rate, that the shear failure occurs with a higher stress rate. Thanks to the results of more than 400 dynamic tests, an example of on samples with different size, shape, notch geometries under different failure mode, a new model was developed. This material model is named DAMP, Damage Propagation Model, where the damage and interfere with the wave propagation, and we have considered this phenomena. This model was used to simulate the blast loading on the sandwich slab, obtaining very good similarity with experimental results. The entire system was modeled by using LS-DYNA, an explicit solver with hexahedral elements. And the experiments were simulated by integrating the constitutive equation of our model with the boundary condition setup of the UHPC and the fiber reinforced material. This slide depicts the damage evolution of the two materials, indicating the color indicated one for a fully damaged and 0 for intact material. And this shows the good suitability of the DAMP model in reproducing our test. Here is the comparison between the stress versus time curve obtained experimentally and numerically for the 3 dimension of samples. The good agreement between the experimental and numerical results is due to the fact that DAMP material model evaluates the interaction between damage propagation, loading wave, and spaceman size. To conclude, to fully understand the dynamic behavior of this material, a comprehensive experimental campaign is necessary to gather information about the material response under various loading conditions and across a wide range of strain rate. For a realistic assessment of a structural response under blast or impact, numerical and analytical methods must be utilized. I'd like to thank our sponsor, Arma Suisse, and all of you for the kind attention.
Thank you so much. So, as we have no time for questions, I thank you once again, Ezio, and we can skip to the last presentation, and then I will call the previous one that was absent. The title is High and Very High Strength Steel under harsh conditions of temperature and loading. The authors are Daniele Forni, Ezio Cadoni, Deborah Briccola, Matteo Dotta, Gianmarco Riganti, and Nicoletta Tesio. Is one of the authors with us, the presenter?
Yes, I'm Daniele Forni.
Good morning.
Good morning.
You can share your screen and start.
Yes, just a second. I will try.
Please.
Desktop. Sorry, I'm not able to do this. Just a second, because I don't know why my screen is not sharing.
There is a button.
Yes, condividi schermo, but
okay.
I don't know why. I can see. I'm not able to share the screen. Oh.
Ce l'hai nell'altra scrivania.
Cosa?
È nell'altra scrivania, forse.
Sì, sì, ma non vedo proprio perché me lo fa condividere. Non mi dà le preferenze di sistema. Microsoft. Ok, Zoom. Just a second. Ok.
Is Daniele with us? We cannot hear you.
Here, just let me try, because
okay.
I switch off the PC.
Okay, okay.
Desktop, condividi. And I hope now you can see my presentation.
Yes, if you want, okay.
Okay, it's working.
Screen, okay, you can start.
Thank you very much.
Welcome.
Okay. So sorry for this problem of compatibility with my Macintosh. I don't know why is happened. So my name is Daniele Forni, and I'm here to present our paper entitled High and Very High Strength Steels Under Harsh Conditions of Temperature and Loadings. In the last year, we can remember different events of this type. For example, the 9/11 terrorist attacks, the Deepwater Horizon disaster, the BASF headquarter disaster, the Rigopiano snow landslide, the highway bridge explosion near Bologna, as well as the Morandi Bridge collapse. The question is, what are the common things among these events? They are all dynamic events characterized by combined effect of actions. They lead, in fact, to a large number of fatalities and high cost for reconstruction and demolition. So the main objective of our project was to understand the mechanical behavior of both structural and reinforcing steels under the combined effect of dynamic loads and temperatures. Today, we will focus the attention on the structural steels named S690 and 960. And you can see, for example, a simulation of a steel column, which I've done. We obtained the samples for the mechanical characterization, as you can see on the top right of the images, starting from the raw section of the material. But we know that the thickness, the material is not homogeneous within the thickness of the material, because we have a peripheral region which has a martensitic microstructure, while the core has a binitic one. For this reason, we obtain two types of samples made of different submaterials from the core and the peripheral zone. And this is the experimental plan we did. So starting from the quasi-static conditions to the high strain rate test at room temperature, then by keeping the same loading condition, we did also the high strain rate test at high temperatures. The dynamic characterization has been performed by using a modified Hopkinson tensile bar in the plus the addition of an induction water-cooled heating system, as you can see on the image. The tests were performed firstly by heating the sample at the desired temperature, and then by keeping the temperature constant for some second or minutes, and then performing the dynamic test. Only at room temperature, due to the shape of the coil, we recorded the failure process by means of an high-speed camera to record the failure process of each sample. In this slide, I have reported some of the different mechanical properties that we can record for each test. For example, the proportional limits at 2%, the strength corresponding to different levels of strains, the ultimate tensile strength, as well the modulus of resilience and toughness. So let me say something about the room temperature test very quickly on this stress strain graph, in which, for the sake of simplicity, we have reported only the peripheral zone for the two materials, so SN690 and 960. We can see the strain rate sensitivity starting from the quasi-static test to the high strain rate test. The strain rate sensitivity is also well represented in these plots, where the dynamic increase factor as the ratio between the quasi-static to the dynamic mechanical properties is depicted. On the left, this ratio is reported for the yield, while on the right is depicted for the ultimate tensile strength, highlighting the different strain rate sensitivity of core and peripheral zones. So, something about the temperature effect. It's obvious, we know, that at increasing temperature, we have a decrease in the mechanical strength. But we have observed in particular that up to 400, 550, so the yellow and the orange curves, we have only a limited decrease in strength. While for higher temperature, let me say starting from 700 Celsius, the decrease is more evident, while and also the total elongation, as you can see on the red curves. This is also well represented in these two 3D surface plots, where both yield on the left and the ultimate tensile strength on the right have been can be represented. So to say something about the material models, we can say that, and we know that there is an increasing demand for complex numerical simulations of civil engineering structures. This is to evaluate the structural robustness under extreme loading conditions, for example, of high temperature and dynamic loads. The link between the mechanical properties and a numerical simulation is a material constitutive law. So we have considered three different approaches. The first one is by calibrating the experimental test results with the elastic elliptic perfectly plastic model proposed by the Eurocode 3, but under dynamic conditions. And the last two are the commonly constitutive relationship describing the mechanical properties of metallic materials at high strain rates. We know the names are the Cooper-Simon and the Johnson-Cook relationships. The choice amongst these three approaches can depend of different aspects. For example, the problem to be simulated, or in the case of the last two, because I'm talking about Cooper-Simon and Johnson-Cook constitutive material model, because they are the most commonly implemented and easy to use constitutive relationship in the finite element programs. So in the first case, so for the elastic elliptic perfectly plastic approach of Eurocode 3, we have reported an example of the 690 at 250 strain per second, and we can see that the model we have calibrated can safely predict the real mechanical behavior of the material in the range of the strain and the stress reported on the code. So something about the other two models, because the Johnson-Cook models, by means of the 5 constitutive parameters, is able to predict the true stress versus true strain in a wide range of strain rate and temperature. As you can see on the right plots, this model is able to fit very well the experimental data. On the other hand, with the more simple Cooper-Simon constitutive model, is it possible to, by calibrating only 2 parameters, to predict the yield tensile strength at increasing temperature, but in its original formulation only at room temperature. So to conclude, we have investigated 690 and 960 structural steel as a part of this investigation campaign to reveal more information and facilitate their widespread use. Following a multi-hazard approach for the civil engineers, we have highlighted the necessity of understanding the mechanical properties of materials under coupled effect of extreme actions. From the experimental test, we can say that the materials are strain rate sensitivity both at room temperature, and the main properties at high temperature have been highlighted. And lastly, we can see that the three approaches of the models were able to fit the experimental data, we can say, very well. As a feature development in the last seconds, we would like to study also the green area in which the strain rate is in the medium range. So for example, for earthquakes, but also at different temperatures. We can go to study also other structural steels, for example, 235 and 460 steels. And of course, one of the more important feature development can be to study the effect of ductile to brittle transition, for example, by testing a temperature below 0 Celsius, of course, under dynamic conditions. And this is all for me. Thank you for your attention, and excuse me again for the beginning of the presentation with the error of the sharing of the screen.
Thank you for your presentation. And as we are a bit late, we have no time for questions. And thank you once again, Daniele. And I'm recalling the authors of the work simulation of the flow in a fractured rock: Al-Mukhtar, Goma, Arafat, and Menzul. Is one of them with us? I think not. So the section is ended. Thank you to to all the presenters, and now that there is the lunch, and next there is the starting of the in presence sections. So see you later. Goodbye.
Bye.
Bye.
Bye.